The year is 2154. Our planet has been ruined by environmental catastrophe. In the movie Avatar, greedy prospectors from Earth descend on the world of an ancient hunter-gatherer people named the Na'vi. Their home is a lush moon far beyond our solar system named Pandora. Could such a place exist? And could our technology and our appetite for exploration one day send us hurtling out to reach it? In fact, the supposed site of this fictional solar system is one of our most likely real interstellar targets, until a better destination turns up. Pandora orbits a fictional gas planet called Polyphemus. Its home is a real place, Alpha Centauri, the brightest star in the southern constellation of Centaurus. At 4.37 light-years away, it's part of the closest star system to our Sun. Alpha Centauri is actually two stars, A and B. One slightly larger and more luminous than our own Sun, the other slightly smaller. The two stars orbit one another, swinging in as close as Saturn is to our Sun, then back out to the distance of Pluto. This means that any outer planets in this system, anything beyond, say, the orbit of Mars, would likely have been pulled away by the companion and flung out into space. For this reason, Alpha Centauri was not high on planet hunters' lists, until they began studying a star 45 light-years away, called Gamma Cephei. It has a small companion star that goes around it every 76 years. Now it seems it also has at least one planet. That world is about the size of Jupiter, and it has planet hunters excited. Perhaps 2/3 of all the stars in our galaxy are in so-called binary relationships. That means there could be many more planets in our galaxy than astronomers once assumed. At least 3 teams are now conducting long-term studies of Alpha Centauri, searching for slight wobbles in the light of each companion star that could indicate the presence of planets. If they find a planet that passes in front of one of the stars, astronomers will begin intensive studies to find out what it's like. One of their most promising tools will be the James Webb Space Telescope, scheduled for launch in 2014 or 2015. From a position 1,000,000 miles away from Earth, it will deploy a sun shield the size of a tennis court and a mirror over 21 feet wide. The largest space telescope ever built, it will offer an extraordinary new window into potential solar systems like Alpha Centauri. With its infrared light detectors, this telescope will be able to discern the chemical composition of a planet's atmosphere. And perhaps whether it harbors a moon like Pandora. One prominent planet hunter predicted that if a habitable world is found at Alpha Centauri, the planning for a space mission would begin immediately. Here's that star duo seen by the Cassini spacecraft, just above the rings of Saturn. To actually get to this pair of stars, you'd have to travel as far as the orbit of Saturn, then go another 30,000 times further. Or put another way, if the distance to Alpha Centauri is the equivalent of New York to Chicago, then Saturn would be just 1 meter away. So far, the immense distances have not stopped us from launching missions into deep space. In 1977, the twin Voyager spacecraft were each sent on their way aboard Titan III Centaur rockets. After a series of gravitational assists from the giant outer planets, the spacecraft are now flying out of the solar system at about 40,000 miles per hour. They're moving so quickly that they could each whip around Earth in just 45 minutes. twice as fast as the International Space Station. Voyager 1 has now traveled over 110 astronomical units. That's 110 times the average distance between Earth and Sun, or about 10 billion miles. But don't hold your breath. If it was headed in the right direction, it would need another 73,000 years to travel the 273,000 astronomical units to Alpha Centauri. When it comes to space travel, we've yet to realize the dream forged by rocketeers a century ago. A Russian schoolteacher, Konstantin Tsiolkovsky, inspired generations of space visionaries with sophisticated ideas about multi-stage launch vehicles. He imagined the construction of space stations in Earth orbit, and eventually vast permanent space colonies. In time, he predicted, we'd evolve into a whole new species, Homo cosmicus. Since then, rocketry's greatest advances have centered on ways of containing explosive propellants and methods of maintaining stable flight at high speeds. The problem is that chemical rockets are just not efficient for long-distance space travel. To reach the speed needed to enter orbit around Earth, 17,500 miles per hour, the space shuttle must carry 15 times its weight in fuel. And that's efficient compared to some other rocket systems. And you'd need to be traveling more than 25,000 miles per hour to break free of Earth's orbit and go anywhere else. A NASA study showed that to send a space shuttle-sized craft to Alpha Centauri in 900 years would take an unbelievable amount of fuel, 10 to the 137th kilograms of rocket propellant. Suffice to say, it's more mass than is in the entire visible universe. While only a very tiny percentage of NASA's budget goes to advanced propulsion, there are some promising ideas on the drawing board. Rockets powered by nuclear fuel, or plasma, a supervolatile gas. Huge sails pushed along by the pressure of photons from the sun. Ion drives. But to reach Alpha Centauri within a human timescale, we'll have to go with the most potent fuel in nature that we currently know. It's the science fiction fuel of choice, antimatter. In James Cameron's Avatar, hybrid nuclear fusion and antimatter engines power a mile-long interstellar spaceship. At a speed of 670 million miles per hour, this vehicle makes the journey to Alpha Centauri in just 6 years. Antimatter really does exist, as the mirror image of the universe we know. It consists of electrons and protons, but with their electrical charges reversed. Whenever it comes into contact with normal matter, the two annihilate each other in a ferocious blast of energy. Large amounts of antimatter were created and destroyed in the fiery dawn of our universe, the Big Bang. But somehow, in one of the great mysteries in science, we were left with a universe whose visible substance is almost all normal matter. The universe still produces antimatter through powerful collisions, such as a jet from a black hole slamming into a cloud of gas. When matter and antimatter obliterate one another, they emit gamma radiation that we can then detect with instruments such as the Fermi Gamma Ray Space Telescope. Fortunately, black holes aren't the only way to generate antimatter. In giant labs, like the Large Hadron Collider, scientists accelerate atoms to nearly the speed of light and blast them together to expose their fundamental constituents. Small amounts of antimatter can be made this way, but it's incredibly expensive. With a dedicated facility, the cost of producing it might come down far enough to produce usable amounts. And that's the hope of one researcher. Dr. Gerald Smith has been working for over a decade to find a way to trap this volatile substance and store it in isolation from the rest of the universe. Smith and his colleagues have designed a trap the size of a cigar case. It sits within a tank filled with liquid nitrogen and liquid helium, designed to cool it down to 270 degrees below zero. Once injected into this trap, antimatter particles are suspended by magnetic fields within a vacuum as empty as deepest space. But the problem is that anti-electrons, called positrons, tend to repel each other explosively. That makes it tough to store more than a few at a time. This team now believes it may have discovered a pathway to storing large amounts over longer periods of time. Their solution lies in combining positrons with electrons, forming an element called positronium. In theory, with the right magnetic fields, these electrically neutral atoms might be held indefinitely. When released under controlled conditions, ultra-high energy antimatter beams could turn out to be ideal cancer killers, or lead to revolutionary industrial applications. Or perhaps, one day, they could power long-distance spaceflight. It wouldn't take much. Antimatter is so potent that it defies common sense. A chunk the size of a small coin could propel the space shuttle into orbit. Smith estimates that once in low Earth orbit, a human mission to Mars would take as little as 10 milligrams worth. The basic idea of an antimatter rocket is simple. A beam of positrons is released into the engine core, where it annihilates the surface of a metal plate. That creates an explosion that propels the craft forward. Another design uses a sail. A cloud of antimatter particles reacts explosively to its surface, propelling it forward. Short of traveling to another solar system, there may be good reasons to contemplate developing antimatter propulsion. A preliminary mission would speed beyond the orbit of Pluto, sending back close-up images of dark planet-like objects that ring the solar system out in the Kuiper Belt. A longer-distance probe could reveal new details about the Oort cloud, a vast realm of comets that envelops the solar system. Once out there, it could sample particles that make up the interstellar medium, or send back unique data sets on dark matter, the invisible stuff that makes up the overwhelming portion of our universe. To make it all the way to Alpha Centauri within 50 years, an antimatter probe would have to gradually accelerate to around 10% the speed of light. That's 67 million miles per hour. It would then gradually decelerate as it approached its destination. At those speeds, hitting even a grain of dust could destroy the spacecraft, so it might be best to slow the journey down to a century or more. It's safe to assume for now that we would only send a probe to Alpha Centauri if we discovered a habitable world. There may be other choices in our solar neighborhood. They include Proxima Centauri, a red dwarf star 4.2 light-years away that may be gravitationally bound to Alpha Centauri. Beyond that, not quite 6 light-years away, is Barnard's star. Or there's Lalande 21185, a red dwarf 8.3 light-years away. we already know it has 2 Jupiter-sized planets. There are at least 22 stars within 12 light-years of Earth. And any way you look at it, the first interstellar voyage will be a quantum leap for humanity. The urge to reach out to distant horizons, to climb the highest peaks, to push ourselves past our perceived limits, seems to be a vital part of what makes us human. Yet, explorers of old set off not just because it was there. At times it was greed, hunger, fear, or despair that propelled them outward from their homelands and allowed them to endure their long journeys. Whether we attempt to make this leap to the stars may come to depend on how we regard this planet. To the physicist Stephen Hawking, the journey is imperative. "I don't think the human race," he said, "will survive the next 1,000 years unless we spread into space. There are too many accidents that can befall life on a single planet." Indeed, we can't foresee the impact of wars, social upheaval, or the course of human civilization in coming centuries. But today, we can see the often conflicting trends that could one day propel us out into the interstellar void. On one hand, the technological advances that might make such a mission possible could revolutionize many other aspects of life on this planet. The ever-increasing rate at which numbers of transistors can be placed inexpensively on computer microchips has become a metaphor for the advance of all technologies in this century. From a few thousand transistors on the first printed circuits of the 1970s, computer chips now have billions etched onto their surfaces. Even that number could seem amazingly small in another few decades. Many observers forecast a steep rise, even an acceleration, in the pace of invention and basic research, and for whole new solutions to the problems of energy, food production, health, and more. On the other hand, major periods of scarcity may loom. In the 20th century, the world saw the largest increase in its human population, from less than 2 billion up to 6 billion. The world's population is now around 6.8 billion. It's expected to reach 9 to 10 billion by the year 2040, with the biggest gains in Asia and Africa. According to a recent UN report, the world will have to produce 70% more food by the year 2050, and at least that much more energy to sustain its population. The scarcity of just simple clean water in some regions is already frightening. Now throw in environmental impacts, like rising sea levels, or the spread of deserts linked to a gradually warming climate. The culprit, to most scientists, is rising emission of greenhouse gases like carbon dioxide since the start of the Industrial Revolution. This map charts rising temperature readings from the year 1885 through to the present. In some places they've gone up by as much as 2.5 degrees Fahrenheit. Computer models project the trend out to the end of this century. Depending upon population growth, energy use, and conservation, temperatures could rise anywhere from 2 to 11 degrees more. Will technological advancements allow us to halt the degradation of our natural environments and increase the carrying capacity of our planet? Will we find ways to mitigate the impacts of war, natural catastrophes, or political upheavals? No doubt, if or when we launch our first mission beyond this solar system, the occasion will spur reflection on who and what we have become as a people, as a planet, just as the first missions to the moon and our neighboring planets once did. At first, we'll send a probe designed to relay basic information on what's there. on a world whose light we have only studied from afar. As this cosmic emissary makes its way across the void, we on Earth will continue to struggle in our pursuits of happiness and prosperity, or of mere survival. When it arrives, we'll scan the data for evidence of a world like our own, one that may harbor life. How will our perspectives on that world, and upon our own, have changed?
In the 75 years since then, our close-up views of Pluto and its giant moon Charon still only come from the artist's imagination. Every other planet has been visited by NASA spacecraft, and the post office has issued stamps to commemorate their close encounters.
Of course, for Pluto, because there have been no mission to Pluto, the U.S. stamp says not yet explored. We aim to see a new stamp issued.
We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond.
January 19th, 2006. NASA's New Horizons mission to Pluto successfully lifts off from Cape Canaveral, traveling faster than any previous spacecraft. In just 9 hours, New Horizons passes the orbit of the Moon and begins a 9-year voyage to Pluto. February 28, 2007. The spacecraft zooms past the giant planet Jupiter, getting a 9,000-mile-per-hour gravity assist and cutting 2 years off its journey.
Spacecraft is outward bound from Jupiter, and we're on our way to Pluto.
Congratulations. All right.
The Jupiter flyby was a dress rehearsal for Pluto.
We got the night showing.
Oh, wow, look at that.
Oh, yeah.
New Horizons science instruments return detailed images of Jupiter's clouds, moons, and rings. If all continues well, things look good for July 2015 and the Pluto flyby. In the past decade, humans have been making amazing discoveries in the outer solar system.
The very first thing I did is grab my telephone and called up my wife, and I said, I found the 10th planet.
But astronomers continue to debate the definition of a planet and how the new discoveries change our evolving picture of the solar system. So now, the New Horizons mission is perfectly poised to shed light on this question and revolutionize understanding of our cosmic neighborhood. It's the ultimate in discovery and exploration.
We have no idea what the surface of Pluto looks like. So we could see craters, we could see geysers, we could see patches of frost. This is purely speculation. We have no idea what we're really going to see.
Late 2005, the long journey begins. Cape Canaveral, Florida, NASA's Kennedy Space Center. In the Kennedy clean room, the New Horizons spacecraft takes its first short flights. It's just over 2 meters, about 7 feet from the tip of its high-gain antenna to where it joins the rocket, about the size of a grand piano. Fully loaded with fuel, it weighs 1,000 pounds. Not very large or heavy for a planned journey of almost 20 years.
The main difficulty about going to Pluto is that it's so far away. The Earth is almost 100 million miles away from the Sun. Pluto is 30 times that far, 3 billion miles away. To get to Pluto in our lifetimes means it has to go very fast. Its average speed is more than 10 miles per second. And to do that, it had to be light.
One of the unique things about New Horizons is that we built a very light spacecraft and bought a very large launch vehicle. And the combination is ferocious. It gives us a very high flyout speed because we have a very long way to go.
Sprinting away from Earth on launch day, New Horizons crossed the orbit of the Moon in just 9 hours. Apollo took 3 days. The spacecraft reached Jupiter in 13 months. Galileo took 6 years. But even traveling more than 50,000 miles per hour, it will still be 2015 before New Horizons reaches Pluto and Charon.
So it's not that we're dawdling. We have a long way to go.
Why send a spacecraft on such a long and difficult journey into such a challenging environment? For the science team, it's a voyage back in time to see, close up, evidence of how solar systems form from clouds of gas and dust, and how Earth and all the planets were born.
We're going to learn about how planets are built, because what Pluto is a planetary embryo, an object that's partially formed as a large planet, a stage in planetary formation that the Earth went through, that Mars went through, that all the larger planets had to pass through this size scale. But here we see an object that didn't get any further in the case of Pluto.
The National Academy of Sciences rated this mission to Pluto and beyond the most important planetary mission of the decade. That's because New Horizons could rewrite everything we know about the planets of our solar system.
If you think about the solar system, the so-called terrestrial planets, they're rocky objects in the inner solar system. Mercury, Venus, Earth, and Mars have a lot of similarities. Then you step out a little bit further and you get into what are called the gas giant planets. These are huge objects which are dominated by large amounts of molecular hydrogen and helium gas. And that's Jupiter, Saturn, Uranus, and Neptune.
And that was it. We sort of stopped there. And then there was the little misfit Pluto at the outer edge of the solar system. Poor little Pluto, all on its own.
Then in the 1990s came a series of discoveries that changed everything. Researchers found more and more icy objects in a massive region of the outer solar system known as the Kuiper Belt.
And once we discovered the Kuiper Belt, everything sort of fell into place. The understanding that, in fact, Pluto and Charon are members of this other class of objects called the ice dwarfs.
And in fact, we think that these ice dwarfs are the most populous class of planetary body in our entire solar system.
That tells us, from that respect, Pluto's not special. It's got lots of company out there.
Ice dwarfs aren't just far out there. In the early days, 4 billion years ago, they may have had a role in shaping Earth and bringing our planet the materials of which we're made.
The collisions within the Kuiper Belt produce the short-period comets, which then fall in towards the sun and bombard the Earth, sometimes bringing some of that raw material from which life formed and some of the water that's on the surface of the Earth.
This information about the Earth's birth isn't available anywhere else.
So the key part of that big puzzle of how the solar system formed will come from looking at Pluto, understanding its nature, what it will imply about its formation, how it came to be, and everything about it.
Coming up, with New Horizons safely on its way to Pluto, find out what sophisticated scientific instruments are on board to unravel Pluto's mysteries. For this first ever trip to Pluto, the science team wants to find out the basics. What do Pluto and Charon look like? What are they made of? And what kind of atmosphere exists? Their hunch is that all these questions are connected.
With Pluto, if you want to understand the atmosphere, you have to understand the surface. If you want to understand the surface composition, you have to understand the geology. If you want to understand the geology, you've got to understand the atmosphere. It's all tied together, and so we have instruments to study every aspect of Pluto.
The 7 science instruments on board New Horizons are ingeniously designed. They're small and weigh very little. On average, each uses no more power than a household nightlight, and they're intended to work together seamlessly.
We picked names for most of our instruments. We have Rex and Alice and Ralph, and it's just a happy family.
The black and white telephoto camera called Lori will be used for navigation in the months before closest approach and to study Pluto's surface.
This big barrel is a telescope called LORI, the Long Range Reconnaissance Imager. It's our biggest, most powerful camera in terms of resolution power.
The cameras are key. For over 60 years, Pluto remained little more than a dot, as small and dim as a walnut seen from 30 miles away. In the 1990s, even the Hubble Space Telescope showed just a blurry surface. And this true color image is the best we can do with Hubble and advanced computers. Pluto clearly has a varied surface, but whether these are mountains or craters or polar caps remains a mystery. That's where New Horizons wide-angle camera comes in.
We want to get up close and personal.
Ralph is our main color camera. It's also the camera that's going to take our main global maps of Pluto.
We can get in and map at scales of kilometers and sub-kilometers and even down to tens of meters.
Football field-sized resolution at Pluto. We're going to be able to, to see things thousands of times more precisely than what we've been able to do with the Hubble Space Telescope.
Strangely enough, Pluto's surface seems to have about the same brightness as freshly fallen snow on Earth. It appears so dim only because it's so small and very far away. Equally bizarre, Pluto sometimes behaves more like a comet than a planet. When its eccentric orbit brings it closer to the Sun, the surface heats up and produces a denser atmosphere. Ralph's sister instrument, using a different part of the electromagnetic spectrum, will be studying that.
This is the ALICE ultraviolet spectrometer, which will probe the composition of Pluto's atmosphere and also study its surface.
It measures light with a shorter wavelength than what you and I see. We fly past Pluto. That's the antenna direction. We're going to turn, so the antenna is pointed back at Pluto, back toward the Sun. And we're going to watch as the Sun passes behind Pluto, and we're going to see the sunlight get absorbed at these ultraviolet wavelengths, and we can tell what the atmosphere is made out of at these different heights.
As Pluto approaches and retreats from the Sun, it's thought that there are seasons and weather that resurfaces the planet with fresh, bright ices. Some researchers think this is what creates the light and dark regions, but as yet, no one knows. New Horizons hopes to get to Pluto before winter sets in, and the atmosphere freezes back down to the surface as solid ice. Along its 9-year voyage, New Horizons will also be collecting some very important samples of dust.
What's the big deal about dust? We have dust everywhere. Dust in your house, dust outside, dust all out the solar system. Well, dust comes from the grinding up of material that gets shed and left around. In the case of the solar system, we believe that the dust that's flying around the solar system was produced by the grinding up of asteroids, the grinding up of Kuiper Belt objects, the grinding up of ring particles and so on that is left over from the process of not just forming the solar system, but its constant evolution over time.
So the last of the 7 instruments is a special dust counter. But this instrument comes from a very surprising source. Every part, from logo to detectors, was designed entirely by college students.
Its job is to profile the density of dust particles all the way across the solar system for the first time. But the real breakthrough of this instrument, it's the first time that students have been able to build a flight quality instrument on their own and fly it on a mission to a planet.
The students documented their project in behind-the-scenes home videos.
Our final instrument will have 12 of these dust detectors all lined up on a panel about 0.1 meters squared.
Till now, no dust counter has gotten data farther out than 18 times the distance of Earth from the Sun. Design specs from the SDC are twice that and more, lasting decades, traveling billions of miles, surviving temperatures near absolute zero. Even though it's a student project, the dust counter is every bit as robust and serious as the other instruments on board. The students faced review boards of veteran scientists and engineers as part of the design process. Together, the 7 science instruments are the most powerful set of detectors ever sent on a first flyby of any world in our solar system. But making sure the Pluto flyby is successful meant a race against time to launch in 2006. And before they could ship the spacecraft to the Cape, the hardware and the science instruments all have to go through a rigorous test program. For this mission, keeping on schedule was critical.
It's also important that we get there as soon as possible because Pluto does have an atmosphere right now, but it's moving farther and farther away from the Sun, and at some point that atmosphere is going to freeze out.
Although meeting the target launch date is critical, so is making sure that all the hardware works together like a finely tuned machine.
One builds a spacecraft, you build the individual boxes and instruments first, and they go through their own tests, both functionally and then environmental tests. And that's sort of equivalent to the members of an orchestra, each tuning up. But once you build it as a spacecraft, once you've assembled it, then you're playing the symphony. And that's what we've been doing. We've been testing it as a system.
And then we test it again, and then we test it about 5 more times. Once we launch this, we can't go after it with a screwdriver. We can't go fix anything that isn't working. And the test program, the full-up test program, is more than a year long. A big part of the testing that gives us confidence that it's going to work in flight is the environmental testing. So we put it into an environment that's pretty much exactly like it's going to see on its way to Pluto and at Pluto. That includes a thermal vacuum tank where we put it in this big tank, we pump all the air out, it's in a vacuum just in space, then we heat it up and we cool it down just as it's going to see when it's actually in flight.
And it's not just the extreme cold that engineers test for. The launch itself puts huge stresses on the spacecraft.
These rockets, they're gigantic. They shake a lot. If you've ever seen a paint shaker at a hardware store where it mixes the colors into the paint, that's exactly what the spacecraft is going to go through during launch. One of the things we do is we put the whole spacecraft on a gigantic vibration table, a paint shaker, and shake it. And then test it after that, and shake it again and test it again.
Test phases at APL and Goddard have been very intense. We're running a 7-day-a-week, 3-shift-per-day operation.
Nothing was easy. Even getting to Andrews Air Force Base meant fighting traffic. Leaving home for Cape Canaveral and the final critical months before launch, the engineers in charge were a little nervous.
This is definitely high on the stress level curve. Getting the spacecraft moved from Columbia, Maryland, all the way down to the Cape is pretty tough.
Like packing for a long trip, everything you need must come along. Test equipment, spares, tools.
Everything we're doing is the last time we do it. We want to make sure every mold is exactly tight and fastened correctly. Everything's been assembled, tested. The records are kept properly because there's no going back. This is a flight build.
Saturday, December 17th, 2005. Spacecraft and third stage in its closed-up fairing, like a giant fragile egg, are placed on top of a huge transporter. With 9 axles and 81 wheels, it's able to raise and lower itself to roll over bumps and up and down slopes without tilting the cargo. Working round the clock, they arrive at Pad 41 before dawn. "75 years after the discovery of Pluto, 17 years after a mission was first proposed, the dream of exploring the 9th planet was now only weeks from launch."
For most people on the project, in a sense, this is the end because it will be built and launched and on its way. But for the science team and the operations team, this is the beginning. This is where we begin the journey. Like a ship, we launch it.
On January 19, 2006, after nearly 2 decades of planning, building, and testing, a picture-perfect launch thrilled the mission operations team back at Johns Hopkins. But the long journey to understand Pluto actually began 75 years earlier, far away in the American West. The story of Pluto's discovery begins here, Flagstaff, Arizona, the Lowell Observatory. Named for its founder, Percival Lowell, a rich Bostonian who was fascinated first by the possibility of water and life on Mars, and then by the search for Planet X, an undiscovered world out beyond Neptune. Pluto was discovered here, and the observatory remains a center of Pluto research today. Astronomer Mark Bowie personifies the ingenuity and persistence it takes to study Pluto.
Part of why I like Pluto so much, because it's a cold, icy place.
Bowie's role on New Horizons is to help find targets far out in the Kuiper Belt, where the spacecraft will travel after it has flown by Pluto and Charon. This homegrown instrument, named Mimir after a Norse god of wisdom, will be placed on ground-based telescopes to study ices on Pluto's surface before the spacecraft gets there. For 2 decades, Bowie and colleagues have used the best instruments available to map the planet. In the mid-90s, he and Alan Stern collaborated in using the Hubble Space Telescope to make the first direct images of Pluto's surface.
Hubble has revealed the first glimpse of Pluto for the first time. And it's exciting to Mark and I and to our whole scientific team to be able to see this object that no humans really could glimpse as a real planet, as a real object in the solar system previously.
In 2002, astronauts placed the new Advanced Camera for Surveys on board Hubble, and Bowie now had data for a new map.
I think this map is probably the best map we're going to get prior to the spacecraft getting there.
Pluto clearly has dramatically varied geology, though the images are still mysterious. But what a transformation from the dot of light that was Clyde Tombaugh's first sight of Pluto 3/4 of a century earlier. 75 years to the exact day and time, Observatory Director Robert Millis shows us how the discovery was made.
75 years ago, Clyde Tombaugh sat at this machine and became the first person to ever see the planet Pluto.
The machine is called a blink comparator. Tombaugh used it to look at photographs of the same patch of sky taken a few days apart. Night after night, he'd patiently expose the large glass plates. Day after day, he'd blink the plates back and forth, looking for anything different from the fixed points of starlight. Decades later, Tombaugh still recalled just how uncomfortable and challenging the search for Planet X turned out to be.
You get cold, you get numb. It took a lot of perseverance, because this gets brutally monotonous.
Blinking back and forward, Tombaugh was looking for anything that shifted position.
The only means you have identifying a planet is going to be small. It's like a small star image. The only clue you have is it shifts position with an interval of a few days in a night's time. It's the only clue you have. So you've got to see all these star images, hundreds of thousands of them, to see if any of them shift position during the interval between the first and second plate.
That small movement was just what Tombaugh saw on February 17, 1930. The arrows were added to show its position a few days apart. It was just what Lowell and Tombaugh wanted to see, a distant planet. After some debate, an English schoolgirl, 11-year-old Venetia Burney, came up with the name Pluto, god of the underworld. PL, of course, were also Lowell's initials. By studying the motion of that dim and distant dot of light, astronomers discovered a Pluto year, the time it takes to move once around the Sun, was equal to 248 Earth years. The angle of its orbit, seen here in silver, was steeper than any other planet. Its distance from the Sun also varied more than any other planet. For 48 years, that was all anyone knew about Pluto. Then, in 1978, astronomers Jim Christie and Bob Harrington analyzed new plates taken at the U.S. Naval Observatory in Flagstaff. Christie noted an elongation of the planet to the north. 1 month later, the bump had disappeared. Blink the images back and forward just like Clyde had done, and you see the bump is moving. Their conclusion? Pluto, like Earth, has a moon. Christie suggested the name Charon after the ferryman of Pluto's underworld in Greek mythology, but preferred to pronounce it Charon, more like his wife's name, Charlene. From the motions of Pluto and Charon, astronomers could work out that the moon was almost half the size of its planet, so large that both objects spin around a central point, their mutual center of gravity, outside Pluto. Pluto and Charon were the first binary planet known in our solar system. Using the basic physics of their orbits and their distance from each other, astronomers were able to calculate their mass and size. Pluto was smaller than our moon, about 1,500 miles in diameter, and had only 1/10 of its mass. Pluto and Charon together would barely stretch across the continental United States. From its size and orbit, astronomers estimated that Pluto is perhaps half rock and half ice. That makes it one of the largest of a whole new class of objects, the ice dwarfs, living out in what's known as the Kuiper Belt. This region is named for Gerard Kuiper, a leading mid-20th century planetary astronomer. Kuiper suggested that the solar system didn't end with Neptune and Pluto, but that there should be a disk or belt of other worlds somewhere way out there. In 1992, from a mountaintop in Hawaii, David Jewett and Jane Liu found the first Kuiper Belt object. They were using new and highly sensitive CCDs, like the sensors in a modern digital camera. But their technique was essentially an updated version of Tombaugh's work. Take carefully registered images of a patch of sky and see if anything moves against the distant stars. This one, QB1, did just that. Jewett and Liu had found the first Kuiper Belt object. It was just a few hundred kilometers across, about the size of an asteroid. In 2002, Caltech astronomer Mike Brown and colleagues found a Kuiper Belt object half the size of Pluto. In 2004, Sedna, another world, 3/4 the size of Pluto. Brown kept on looking, using computers to do the work of Tombaugh's blink comparator.
We do exactly the same thing. Clyde Tombaugh is the one who basically figured out the system for finding these things. But we do it all by computer instead. These are 3 images in a row that are blinking on the screen, just like Clyde Tombaugh would blink. On the morning of January 5th, 2005, I was looking at these very images, and I clicked the button saying this one's no good, and I suddenly see this object here very clearly moving across the frame in dead center. And this is the one where I almost literally fell out of my chair, because it's perhaps it's close to being the brightest object we'd ever seen out there, and it's also moving extremely slowly. Slow means it's far away. Slow and bright means it's really big. If you combined more distant with anything we'd ever found and almost the brightest thing we'd ever found, you knew immediately that this thing had to be the biggest thing we'd ever found in the outer solar system. The very first thing I did is grab my telephone and called up my wife, and I said, I found the 10th planet.
2003 UB313, the random name assigned by Brown's computer, was 25% larger than Pluto. Until an official name was chosen, Brown came up with a temporary nickname, commemorating Percival Lowell's search for Planet X.
We had actually been reserving the name Xena for the first object that we found larger than Pluto. We wanted something that started with an X for Planet X. We wanted something that was mythological. Now Xena is only TV mythology, not real mythology, but we figured Pluto is named after a cartoon dog, so that's okay. And we wanted something that, we decided there weren't enough female planets, so we were going to name another one female planet. So if you take those 3 together, you get Xena.
Xena has now officially been named Eris, goddess of discord, which seems appropriate. Some astronomers argue that Pluto and Eris, as Kuiper Belt objects, should not be classified as true planets. Others disagree. In August 2006, in a controversial decision, the International Astronomical Union reclassified Pluto, Charon, and Eris as dwarf planets. But Mike Brown thinks the new findings far out in the Kuiper Belt only make the New Horizons mission more exciting.
Pluto is the closest member of this new class of objects we're finding. The next best thing to studying all of these objects out there is to go look at some of the big ones. Go look at Pluto. It's not the biggest one out there, but it's the closest really big one that we can learn a lot about. So I think that going to Pluto is much more exciting today than it was even a year ago.
In 2005, Hal Weaver and Alan Stern used the Hubble for another close-up look at Pluto and Charon.
We want to know everything that could possibly be along our path as we're going through the Pluto-Charon system.
The result was an historic and astonishing discovery.
This was just incredible. In fact, it was so incredible we almost didn't believe it at first.
They saw two small, dim moons where only Charon had been known before. It would double the excitement of the close encounter.
We get 4 for the price of 2. You know, instead of having just Pluto and Charon, we now have another couple of exciting moons to investigate. Pluto is an even more interesting place than we imagined.
Mark Bowie went back and confirmed the discovery by reanalyzing previous images. He made this true color portrait of Pluto and Charon with the newest moons, Nix and Hydra. New Horizons will speed through the Pluto system in less than a day. To maximize success, the mission would use flying by Jupiter, the largest planet in our solar system, as a dress rehearsal for encountering the smallest. Early 2007, engineers and scientists got ready. Unlike missions that go into orbit around their target planet, New Horizons is traveling so fast there's no practical way to slow down. After a 9-year trip, closest approach to Pluto and Charon will flash by in less than a day.
This is going to be incredibly nerve-wracking. As we do the encounter, we get one shot at flying by Pluto. That's both terrifying, also very exhilarating.
Pluto is so far away that radio signals from Earth take 4.5 hours to get there, and 4.5 hours back. This 9-hour round-trip light time means computer commands for every aspect of the encounter, from navigation to operation of the science instruments, must be programmed, tested, and uploaded ahead of time.
It's very scary to build a spacecraft and then launch it and not get any data for 9 years. And so it's really key to test out the instruments before we get there.
June 2005, 10 full years before arrival at Pluto. The mission operations team runs a detailed simulation of the encounter, modeled to the split second. To test the spacecraft still more rigorously, the project decides to use the Jupiter flyby to take actual scientific observations. They'd look at the volcanic moon Io. They'd study Jupiter's cloudy surface and aurora.
This will be a wonderful dress rehearsal for the whole process of putting together a complicated sequence. And we only get to do it once at Pluto, so having this practice at Jupiter will be very valuable for that.
January 2007, still another simulation. The Jupiter encounter has mission planners working harder than ever.
So it's more intense than by several orders of magnitude than anything we've done as far as memory usage, which translates to number of commands.
It's more intense actually than our Pluto simulations we did pre-launch. I guess the usual stuff. Axis normal, our SPE is going to range from 7.056 degrees. The observation starts 10:06:16.
Before any command is sent up to the spacecraft, it's reviewed by a representative of every subsystem, power, thermal, data handling, as well as the science team. One bad line of code can cripple a spacecraft. The Jupiter encounter has 40,000 of them. Every command is run through a series of computers, identical to those up in space, except that this New Horizons mission simulator is safely on the ground in Maryland. February 28, 2007, 45 minutes after midnight, GMT. New Horizons closes in on Jupiter. Hours later, scientists and engineers gather at the Applied Physics Laboratory for what they hope will be the first post-encounter transmission from the spacecraft. Mission managers coordinate with researchers across America. Experienced operators stand by at stations dedicated to each instrument and subsystem. The ACE, or Lead Flight Controller, communicates with NASA's Deep Space Network Station in Australia. Alice Bowman is Mission Operations Manager. or mom. Her professional family includes some of the brightest engineers around.
Today's very important. It's our Jupiter flyby day. And of course, the test is coming right up. We'll see if the spacecraft made it through the dangerous radiation at Jupiter.
For this milestone in the life of the mission, all hands are on deck.
It's real big. As you can see, we have a lot of people coming in today, a lot of scientists who wanted this information off the satellite that we've been trying to get for them. So today is real eventful.
I would put it somewhere between launch and actually getting to Pluto. I'd say it's the third most critical activity in the whole timeline.
We're really putting the spacecraft through a stress test. That's our primary objective. But as long as we had to stress it, we thought we'd stress it with 700 science observations.
700 observations, 40,000 commands. Science planners work with guidance and control engineers to write a playbook for the encounter, a script for every time tick of the flyby. At Jupiter, New Horizons is on her own. Here on Earth, they wait.
You guys nervous?
No, not really.
Nothing we can do at this point.
That's right, not nervous.
Nah.
Not a bit.
This is all done by remote control. That's the nature of this business. 500 million miles away, our little puppy is doing its job and doing very well.
Just come up on track like it always does. So we're about a little less than 6 minutes away from our first look at telemetry.
They'll know all is well when screens light up with green text indicating the spacecraft has survived. DSN Australia confirms that New Horizons has phoned home.
Pluto Ace.
Go ahead, Pluto Ace.
Yes, we're now receiving telemetry and we're logged.
RF mom on Pluto 1. Status check.
RF is green.
PI, this is mom on Pluto 1. Spacecraft telemetry for all subsystems is nominal. Spacecraft is outward bound from Jupiter, and we're on our way to Pluto.
Congratulations. All right.
Oh, relieved. We expected everything to go well, but it's good to know that it really did. Now we still have to wait for the data to come down, see what's happening with the radiation levels on our instruments, and waiting for that really good picture of Io that we should be getting in a couple of hours.
Good. Everything's looking really good at this point. The station's cooperating. No problems with the station. The spacecraft's in a good state. All's well.
Jupiter's not our ultimate destination. It's very nice, that we can actually get a lot of great scientific data for free, basically. We can give gravity a boost, the most important thing, but after that, just getting that extra science and the extra practice for doing an encounter, which are really hairy. These encounter situations where it's all or nothing. You fly by and you don't return. We have to make sure everything works perfectly, so we're going to learn some lessons from this experience, apply them to the Pluto encounter, and hopefully make for, an even better Pluto encounter.
The engineers could tell right away that all spacecraft systems were nominal. But the scientists wanted to see the very first pictures of Io. They'd gotten used to fancy computer graphics depicting an imaginary trajectory and volcanic plumes. But the actual images just in from Jupiter would determine scientific success or failure.
Yeah, this is the highest resolution image of Io with its spectacular plume, we hope.
Like Clyde Tombaugh decades earlier, they hoped for discoveries.
Flight radar. Oops.
The spacecraft took the images hours before, but for the researchers, this was exploration live and real time.
There it is off the, wow. Okay.
Camera and spacecraft delivered as promised.
2 plumes off the limb.
Okay.
Got both.
We got the night shipping.
Oh wow! Look at that.
Oh yeah.
And we got both of them. We got both of them.
And another plume.
Oh my gosh!
Rising into sunlight.
That's right, yeah.
The first raw images might be fuzzy, but now they knew their aim was true. Computers would be able to clean them up and begin to update the textbooks.
Yeah.
Hal and John rushed next door to let the full science team see how their spacecraft was performing.
Second Pluto has a different
Researchers called out requests to adjust brightness and contrast to reveal details hidden in the pictures. Now they knew for sure they'd captured the volcano called Tvashtar, spewing its sulfur plume 180 miles up into space.
How about that one up there?
What is that?
How about this one here? Is that a mountain or is that a...
Many of the scientists were veterans of previous missions, but precise navigation and state-of-the-art cameras were revealing the Jupiter system as never before.
There was the one Voyager 1 image, the high-resolution image that showed the filamentary structure, but nothing like this.
Yeah, that's important.
Professional astronomers, of course, thrill at each new image, but the general public also had a role in targeting New Horizons cameras.
And what we actually did is went out to some blog sites where talented amateur astronomers and planetary scientists discussed the latest findings.
Like the student dust counter, this was the first time the public had a chance to shape a deep space mission.
We asked them, suggest to us some of your best ideas for what we call Kodak moments, unique geometries when we could obtain something evocative.
Out of this process came the idea for snapping Io and Europa lit edge-on by the sun. Stern's favorite captured Europa rising over Jupiter.
It gives you that feeling that you're actually at Jupiter, and you have a view that you might not expect to have from a spacecraft, as if you were actually there, an astronaut making the flyby with New Horizons.
There were 7 Kodak moments, but New Horizons returned almost 700 observations.
And we have very detailed images that show us much finer structure now in Jupiter's ring system than had ever been obtained by any previous mission.
The cameras had been designed to work in the much dimmer light far out at Pluto, but special software helped record the structure and dynamics of Jupiter's clouds, including both the great and little red spots.
No spacecraft had made detailed observations since the formation of the little red spot. And this is not such a little spot, after all. It's as large as the Earth, practically. And we happen to be the first mission to Jupiter since the coagulation of some smaller storms into the so-called little red spot.
So the spacecraft passed this intentionally extreme stress test with flying colors.
Because I would have been very happy if half or more of the observations had worked out, rather than upwards of 95–97%.
Leaving Jupiter, New Horizons will fly down the planet's giant magnetic tail, another first for this mission. Then it will be time for an 8-year cruise to Pluto, with long periods spent in hibernation, instruments turned off.
Well, Cruise for New Horizons is a 8-year sequence during which most of the time the spacecraft is in hibernation. And we do that in part to save money, but more importantly to save time, wear and tear on the electronics. In fact, most of the electronics boxes on New Horizons, although they will be 9.5 years old on reaching Pluto, they will only have between 2 and 3 years of on time. So for practical purposes, the spacecraft is not 9.5 years old, but 2.5 or 3 years old.
Just commands out.
Keeping the spacecraft young is one thing. Mission planners also had to think about who would be around to operate the spacecraft in 2015. Many of the faces you see around New Horizons are relatively young. That's also no accident.
You know, if it's something like that, we should have.
The project wants to make sure key team members are still on the job when the spacecraft gets to Pluto.
How old are you going to be? In 2015?
Yeah.
I don't know, somewhere in my 40s.
Oh, and you're a youngster.
Yes.
If all goes well, even 2015 won't be an end date for New Horizons. It should have enough fuel to travel onwards, to rendezvous with 1 or 2 ice dwarfs beyond Pluto.
3, 2, 1.
The story of New Horizons may be a tale of high-powered rockets and sophisticated science instruments, but it's also evidence of human persistence, passion, and boundless imagination.
It's going to be an almost timeless object, that we're building something that will not only outlast the pyramids, but outlast the mountain ranges of the Earth. This will fly through the galaxy essentially unchanged from the way we build it, and it will be just that way.
Humankind for centuries. They acquired their name after Ferdinand Magellan's expedition circumnavigated the globe in the 16th century, and his crew used these cloud-like objects as aids to navigation. During the Age of Discovery, sailors relied on celestial bodies to reckon their own locations. The two heavenly clouds that attracted the attention of Magellan and his crew have fascinated people ever since. Recently, thanks to observations in the southern hemisphere using the most advanced telescopes, research on the Magellanic Clouds has taken a giant leap forward. The Magellanic Clouds turn out to be astonishing records of the very birth of the universe.
They provide a unique opportunity for studying what happens close to us in the universe, and that actually tells us a lot of things about how the universe formed and how galaxies form.
Astronomers throughout the world are eager to shed light on the Magellanic Clouds, hoping to reveal secrets about the earliest days of the universe. This program follows these stars on a journey of amazement and discovery. What is the true character of the Magellanic Clouds? This has been a huge mystery since the Age of Discovery. By the 17th century, 100 years after Magellan's expedition circumnavigated the globe, Europe was producing numerous star charts of the southern hemisphere. The constellations were pictured as various creatures: a flying fish, a chameleon, a resplendent peacock, a big-billed toucan. The constellations all had exotic names. And then there was Nubecula Major, Latin for large cloud, meaning the large Magellanic Cloud. That was paired with Nubecula Minor, or small cloud, the small Magellanic Cloud. Since they moved together with the stars, they were clearly no earthly clouds. They were heavenly bodies. But exactly what they were remained a mystery. The first detailed research into the Magellanic Clouds began in the 1830s. To conduct research into stars of the southern hemisphere, England had established a royal observatory at the Cape of Good Hope in southernmost Africa. Astronomer John Herschel worked there for over 4 years. He pioneered the study of celestial objects in the southern hemisphere. In 1847, Herschel published his findings in a 450-page report. This is the catalog of objects Herschel found in the Magellanic Clouds. Some 1,000 items are listed. There are numerous records of nebulae and star clusters, similar to those visible within the Milky Way galaxy. Herschel clearly thought of the Magellanic Clouds as constituting a galaxy. At the time, most astronomers thought that all celestial bodies lay within the disk of our own Milky Way. Herschel thought that these rather indistinct and nebulous objects must be extragalactic celestial bodies. To prove that, however, one would have to calculate the distance to the Magellanic Clouds. Alas, Herschel did not possess the means to do that. Are the Magellanic Clouds inside the Milky Way or outside? An epoch-making discovery at Harvard University finally solved the riddle. The crucial evidence was supplied by photographic plates stored here. This is the world's largest archive of astronomical photographs.
As you can see, we have cabinet after cabinet, many plates, 525,000 plates in this collection. That's 25% of the world's total of astronomical photographs just in this collection. And what is remarkable about that is that it covers more than 100 years of time, from 1885 to 1989. And we began photographing the southern skies early in the 1880s, so that the Magellanic Clouds are covered from that early time.
These photographic glass plates recorded light from the stars over long periods of exposure. They enabled astronomers to capture not only what Herschel could see directly, but even far dimmer stars in the nebulae. Around the turn of the 20th century, the data etched on these glass plates were processed by a team of female analysts. The position and brightness of every single star were meticulously recorded. The analysts were actively seeking variable stars, a popular quarry at the time. Variable stars are stars whose brightness fluctuates. Of particular interest were those whose brightness fluctuated in regular periods.
This was one of the very old ones.
This type of star could help prove whether the Magellanic Clouds lay inside or outside the Milky Way.
With the
Wow, it's a 240-minute exposure.
here we have a glass plate of the small Magellanic Cloud, a long exposure which is taken. Some of the stars will be variable stars, but you get them at only one moment on this plate. So this is a negative plate, and we also can then make from one of these plates a positive plate. And this one can then be used as a master. When you put them on top of each other.
Superimposing an image of a given area on top of another taken at a different time reveals any change. If the star's brightness is constant, it should be a perfect match. What happens when the brightness changes? Since brightness is translated optically as size, any variability is immediately apparent. This comparative method, done plate by plate, is a way of detecting which stars are variable. One of Harvard's female star analysts was Henrietta Leavitt, an astronomer later recognized for her analyses of variable stars. This is one of the photographic plates of the Magellanic Clouds that Leavitt analyzed. Out of 100,000 stars recorded on a single plate, she endeavored to identify the variable ones. Harvard still has her handwritten logbook. She assigned numbers to each variable star, comparing readings at fixed intervals and determining the periodicity of its variations in brightness. To prevent any mistaken attributions among the countless stars in the sky, she drew detailed star charts. After 4 years of research, Leavitt published her study of 1,777 variable stars in the Magellanic Clouds. In the course of compiling these data, she made a vital discovery. She noticed that variable stars in the Magellanic Clouds with the same period had the same brightness, or luminosity. Compared with variable stars of the same periodicity within the Milky Way, the ones in the Magellanic Clouds appeared fainter. The fainter the star, the farther away it must be. In the late 1920s, after Leavitt had passed away, detailed analyses revealed that the Magellanic Clouds lie far outside the Milky Way. Precise observations determined that the Magellanic Clouds are 200,000 light-years away. That's twice the diameter of the entire Milky Way. The Magellanic Clouds were definitely other galaxies lying outside the Milky Way. A large telescope subsequently revealed a deep relationship between the Milky Way and the Magellanic Clouds. This is the 2.5-meter Hooker telescope at Mount Wilson. This telescope enabled measurement of the distances to many galaxies outside our own. It revealed features of the Magellanic Clouds that differentiated them definitively from other galaxies. This is the galactic distribution, as currently understood. The two Magellanic Clouds lie approximately 200,000 light-years away from our own Milky Way. The larger one is approximately 1/10 the size of our galaxy. The nearest spiral galaxy to our own Milky Way is the Andromeda Galaxy, some 2.3 million light-years away. That's 10 times farther away than the Magellanic Clouds. So the Magellanic Clouds are two small galaxies very near our own. Edwin Hubble, the leading astronomer of his day, described the Magellanic System thus. The cloud is an independent stellar system and a close neighbor, actually a satellite, of the galactic system. A satellite is a space object that is gravitationally attracted to another and orbits it, as the Moon does the Earth. Hubble thought that the Magellanic Clouds similarly orbit the Milky Way galaxy. This concept of a satellite galaxy eventually became the standard view among astronomers. A major discovery was made in the southern hemisphere, in Australia. The two Magellanic Clouds together make up a single gigantic space object. The discoverer was an Australian astronomer named Don Mathewson.
If this object I discovered was actually visible, everyone would be astounded. It's an enormous arc of gas stretching right across the sky. In fact, it's more outstanding than the Milky Way galaxy.
Mathewson's starting point was a research paper written by astronomers at Bell Laboratories in the United States. Their measurements of intergalactic radio waves revealed filaments of gas in the skies over the northern hemisphere.
It was a rainy Sunday afternoon, and it was quite late, and I was just turning the pages of an astrophysical journal. I plotted their filament of gas, this sausage of gas, and I thought, well, let's extend that sausage a little bit, let's blow it up a little bit. So I drew a line on this polar graph paper, and I thought, gee, it passes through the large and small Magellanic Cloud.
The line Mathewson extended into the southern hemisphere from the mystery gas mentioned in the article went right between the Magellanic Clouds. And Australia had a radio telescope well suited to confirming the presence or absence of gases. It was the Parkes Observatory. Mathewson couldn't contain his excitement. He telephoned the observatory right away. The very next morning, Mathewson jumped into his car and drove to the observatory. The director had told him that the telescope would be offline for maintenance that day, so Mathewson thought that at night there might be a chance for some brief observations. It took him 4 hours to drive to the Parkes Observatory. At the time, this giant 64-meter diameter parabolic antenna made Parkes the largest radio telescope in the southern hemisphere. When Mathewson arrived, he asked the maintenance workers if he might borrow some time on the telescope.
So all the memories come flooding back, because it was the most emotionally charged episode in my life, really. the discovery of the Magellanic Stream.
Past 10 p.m. It was only after the maintenance staff had left for a late supper that Mathewson was able to use the telescope.
Had it all plotted out, what I thought would happen. But of course in science things never happen the way you want it to. Nature is a very, is a teaser. It teases you and then all of a sudden drops you flat on your face. But tonight was completely different. For the rest of the 3 or 4 hours that it took, every position that I looked at with the telescope came out to be the right velocity and the right intensity.
When the telescope was pointed along the extrapolated path of the gas stream first noticed in the northern hemisphere, further traces of gas were found along the way. The gas trail seemed to be headed for the Magellanic Clouds. That's how Mathewson was the first in the world to actually establish a link between the gas trail and the Magellanic Clouds. Subsequent detailed observations confirmed that their distributions were aligned. This intergalactic belt of gas was named the Magellanic Stream. The Magellanic Stream is an extension of the same nebulae spotted by Ferdinand Magellan. It's a huge belt of gas, stretched out as if to curve around the Milky Way galaxy. It's 1 million light years in length. That's 10 times the diameter of the Milky Way. Like the contrail of a jet plane, the Magellanic Stream is proof that the Magellanic Clouds have passed that way. The gas is distributed as if it were encircling the Milky Way. So astronomers believe that the Magellanic Clouds are spewing out gas as they orbit our galaxy. The Magellanic Clouds, galaxies with a gas trail longer than the diameter of our own galaxy. To people of the northern hemisphere, the night sky of the southern hemisphere presents a strange spectacle. There's the constellation Orion. But it's upside down. And the Milky Way looks huge. The exceptionally bright area is our galaxy's nucleus. In the southern hemisphere, the mysteries of the universe seem all the closer. This is Santiago, the capital of Chile. It's surrounded by 5,000-meter-high mountains. Still bearing traces of its Spanish colonial past, Santiago is today at the forefront of astronomical research. On the way to a green grocer's in a new part of town.
Hola. Gracias.
The shopper is Valentin Ivanov, an astronomer who was born in Bulgaria. Recently, he has been analyzing observations of the Magellanic Clouds made with one of the world's most advanced telescopes. He is affiliated with the European Southern Observatory, known as ESO. ESO has established 3 observatories in Chile from which to survey the stars of the southern hemisphere. With his telescopic observations, Ivanov has been creating the most detailed picture yet of the Magellanic Clouds.
VISTA is one of the newest projects of ESO, and it aims at creating large uniform maps of the sky. These are called surveys. One of the most important surveys that this telescope is producing now is the survey of the Magellanic Clouds, these green squares over here.
To produce a complete map of the Magellanic Clouds, Ivanov spends a total of 1/3 of every year at a mountaintop observatory. He has already taken over 100 of these trips. His destination is about 1,000 kilometers north of Santiago. It's in an arid zone that sees less than 10 millimeters of precipitation annually. This is the European Southern Observatory's largest site. Seven telescopes are located on the mountaintop here, at an elevation of some 2,600 meters. This is the one Ivanov uses. It's a 4-meter aperture telescope called VISTA. Installation was completed toward the end of 2009. Its technology is cutting edge.
VISTA is a special purpose-built telescope. Unlike other ESO telescopes, VISTA is designed to cover extremely large field of view in a single pointing. The field of view of VISTA is about degree by degree and a half.
How does VISTA compare in this regard to the Hubble Space Telescope? VISTA's field of view is about 500 times greater than Hubble's. In a single pointing, VISTA can take in a region much broader than a full moon. Ivanov and his VISTA team are attempting an exhaustive survey of the entire region containing both the small and large Magellanic Clouds and the bridge linking them. It's sundown. VISTA can now be engaged. In the control room, Ivanov will conduct observations all night long. The display shows stars within the Magellanic Cloud system.
The Vista Magellanic Cloud Survey already completed a number of tiles, and the data are publicly available. This data contain a lot of interesting objects, like this giant H2 region called Tarantula.
The Tarantula Nebula is an expansive gas located within the Large Magellanic Cloud. It's 1,000 light-years across. Its name derives from the hairy, spidery appearance of its gases.
This image that we see here actually is built from 3 different images, each of them in the near infrared. The advantage of the near infrared and the advantage of the kind of data that Vista delivers to us is that we can actually see through the dust. If you look at this region, this area on the sky in the optical, you'll see almost no stars because the dust and that absorbs the optical light much more than the infrared light.
Vista captured this image of the Tarantula Nebula. Compare it to an optical image showing ordinary visible light. It's clear that the Vista image reveals the stars hidden beyond the gas and dust. The Large Magellanic Cloud is said to contain as many as 20 billion stars. Vista captures them in stunning detail. Innumerable stars, nebulae, star clusters, countless points of light beyond the reach of ordinary optical telescopes, rendered here vividly and distinctly. Vista is continuing to survey the Magellanic Clouds at a level of detail unmatched by any other telescope. The Hubble Space Telescope has shown us how different in shape as well the Magellanic Clouds are from our own Milky Way galaxy. This nebula, in a remote part of the Large Magellanic Cloud, shines with extraordinary luminosity. It's gigantic, more than 30 times the size of the Great Orion Nebula. And out of the dark gas and dust, it is birthing countless new stars. One region in the Large Magellanic Cloud is giving birth to more stars than any other region in the Milky Way. Here is just one portion. Newly born stars illuminate the surrounding gas. It looks like a cocoon. Here, an accretion of gas and dust is displayed in silhouette, lit from behind by young stars. The largest mass looks like a seahorse. It's a huge object, some 20 light-years in length. The Small Magellanic Cloud also boasts magnificent nebulae and star clusters. The explosive birth of 100,000 stars. The energy they put out is said to be 60 times that of the Great Orion Nebula. Or look at the outskirts of the Small Magellanic Cloud. Innumerable young stars, born all in a group. And this sparkling, multicolored, open cluster has been called the Jewels of Magellan. Even today, the Magellanic Clouds are far more prolific than the Milky Way in the production of new stars. The Magellanic Clouds had been thought to be orbiting the Milky Way. But recently, a great discovery was made in that regard. The discovery was made by Roland van der Merel. Van der Merel spent 4 years directing observations of the Milky Way by the Hubble Space Telescope. His goal was to determine the mass of our galaxy, and he found a way to use the Magellanic Clouds to do so.
We thought that if we could measure exactly how the clouds are moving in the sideways direction, we could learn more about the mass of the Milky Way and about the distribution of the mass in the Milky Way.
Van der Merel's group thus observed the Magellanic Clouds directly in order to ascertain the speed of that sideways motion relative to the Milky Way. As a reference point, they chose to use a quasar, celestial bodies that are very far away and so essentially motionless. By using a quasar located beyond the Magellanic Clouds, as seen from Earth, they could measure the cloud's relative motion. They pointed the Hubble Space Telescope in that direction. The anticipated motion of the Magellanic Clouds was minute. It is the equivalent of observing a 1 millimeter movement from 100 kilometers away. That was close to the limit of Hubble's powers of resolution.
And then if you try this with a telescope on Earth, you run into several realistic problems with telescopes on Earth. For example, telescopes are subject to gravity. As the telescope moves, the gravity on the telescope is different, and the instrument distorts a little bit. And you see this in your images.
The observations with Hubble continued for 4 years.
Now, we cannot actually measure the motions of stars in the Magellanic.
Van der Merel's group succeeded in obtaining data on 25 of the regions into which the Magellanic Clouds had been divided. After analyzing the results for a full year, they calculated that the Magellanic Clouds are moving at an incredible 378 kilometers per second, 1.36 million kilometers per hour. This was 300,000 kilometers per hour faster than anticipated.
Initially, we were just very happy we were getting any results out that said, hey, we can actually measure the motion of the Magellanic Clouds. So that was our initial excitement for quite a while. And it was clear we were doing it better than anyone else had done it before, but it wasn't immediately obvious what we were learning.
To extract meaning from these speed calculations, computer simulations were conducted of the relative motion of the Milky Way galaxy and the Magellanic Clouds. The simulations were carried out at Harvard University. The movements of the Magellanic Clouds were minutely calculated, using the latest data on the size and mass of the Milky Way. This is the result. Contrary to expectations, the Magellanic Clouds do not orbit the Milky Way. Assuming the Milky Way is not unnaturally massive, the Magellanic Clouds will eventually fly off into deep space.
I basically computed things like the escape speed, which refers to the the speed that an object would need to have to escape the potential of the Milky Way at its distance of separation from the Milky Way. And for the basic model that I had initially started off with for the Milky Way, the LMC was sitting at the escape speed. So the orbit couldn't be anywhere close to what we thought before.
So it was very normal for people to think for years that the Magellanic Clouds had been going around the Milky Way many times. Cortina realized that that couldn't be at that speed. They were going too fast. They were basically flying away from the Milky Way too fast, which means that probably they were just coming into the Milky Way for the very first time. And this was a very revolutionary thought.
So the Magellanic Clouds are not satellite galaxies of the Milky Way after all. They are visitors from afar, merely enjoying a chance encounter with our own galaxy. In a few billion years, they are fated to disappear into the furthest reaches of space, never to return. The true nature of the Magellanic Clouds is gradually emerging, and astronomical observations indicate that the clouds hold a key to understanding what the universe looked like right after the Big Bang. Paul Crowther is one of the scientists fascinated by the Magellanic Clouds. For 15 years, he's been studying one of the cloud's features in particular. What's attracted his attention is the Tarantula Nebula. At its center, there's a place estimated to shine with the luminosity of 100 million of our suns. R136 is its scientific designation. It was thought to contain a mystery object. Crowther set out to find out what that was. He conducted his observations with what's called the VLT, or Very Large Telescope, located in Chile. He pointed the VLT and its 8.2-meter diameter mirrors straight at R136 in the middle of the Magellanic Clouds. This is the very center of R136. The detailed view provided by the VLT reveals that what looked like one bright clump at its center is comprised of many stars, the brightest of which has been designated R136A1. With a luminosity of 10 million suns, it is, so far as we now know, the brightest star in the universe. Crowther performed a spectral analysis of its light.
The spectrum is kind of like the fingerprint of an object. It tells us what it's made of, it tells us how hot the gas is in the star. And so this actually is an infrared spectrum taken with a very large telescope of R136A1, and it reveals the presence of, for example, this is a line of helium-2, ionized helium, and this means the star is incredibly hot.
Thanks to this analysis, Crowther was able to start profiling his mystery object. This is how Crowther envisions R136A1 in the center of the Tarantula Nebula. With surface temperatures reaching 55,000 degrees Celsius, it burns bright blue. When it was born, it had the mass of 300 of our suns. To date, nothing comparable has been found in the Milky Way. These first-generation stars of the early universe, born right after the Big Bang, were unlike most of the stars we see today. They were formed directly out of hydrogen and helium gases, and they were all blue giants. In the Magellanic Clouds, there are many such stars. The Hubble Space Telescope has captured a number of ancient galaxies that contain these blue giant stars. All these galaxies are more than 13 billion light-years away. So what we see now is how they looked 13 billion years ago. In other words, just moments after the universe was born. Ancient galaxies, glowing bright blue. The sheer number of blue giant stars, similar to the one Crowther has been studying, is enough to impart a blue color to the galaxy as a whole. These galaxies, born just after the creation of the universe, are a mere tenth the size of the Milky Way and have irregular shapes. In size and shape, they resemble the Magellanic Clouds. That is why scientists believe that studying the Magellanic Clouds will provide insights into the evolution of our own galaxy.
Well, so the interesting thing here is that we've learned a lot about structure formation in the universe over the years. And in particular, what has been learned is that structure forms by smaller units coming together. So if you're a big galaxy like the Milky Way, you really started out as lots of little clumps that fell together over time.
One scenario for the growth of the galaxy would go as follows. In the earliest stage of the universe, there were only small, irregular galaxies like the Magellanic Clouds. These small galaxies collided and merged repeatedly. In this way, so the theory goes, over the course of billions of years, larger galaxies like our Milky Way were formed. Van der Merel believes that the Magellanic Clouds are in fact holdovers from the earliest days of the universe, small galaxies that only now are brushing past our own larger galaxy.
In the early universe, soon after the Big Bang, we believe this happened all the time. There were bits and pieces of galaxies falling together to form the first real galaxies that then later grew over time. Nowadays, in our current universe, this is actually a pretty rare occurrence. So the fact that we're seeing the Magellanic Clouds pass the Milky Way right now is very unusual at some level, but it really gives us a glimpse of what the universe was like more typically when it was much younger, when galaxies were falling onto each other and merging together all the time.
The Magellanic Clouds had been thought of as satellite galaxies. But it turns out that they are actually leftovers from the very beginnings of the universe. Small galaxies linked together, spewing a plume of gases behind them as they rush past us. At the Vista Telescope in Chile, observations of the Magellanic Clouds are ongoing. The detailed mapping of the Magellanic Clouds, based on the VISTA surveys, is expected to be completed in 2017.
VISTA is continuing the observations of the Magellanic Clouds, and we are extremely lucky to have this exciting and mysterious galaxy next to us, because it has been a wonderful playground for astronomers for more than a century now, couple of centuries, and I'm sure it will help us to reveal many more secrets.
The origins of the universe, the birth of the galaxies. These are the mysteries to which the Magellanic Clouds hold the keys. As humanity peers into the southern night skies, that quest will continue.
Checking out traffic this morning along the Huey Gardner, Guy Valentine.
It's a bit of a battle for drivers without cover. I'm talking if you don't have any shades, you're fighting some pretty bright sunshine.
Also caution on Highway 7 going east and northbound Don Valley Parkway on the ramp to eastbound 401. We've got a disabled vehicle.
June the 14th, 2002. It was just another busy workday with all the usual hustle and congestion. With all the close calls and near misses that people all over the world have come to accept as the normal level of risk in everyday life. But on that day, high overhead and behind the sun, what no one saw coming, what no telescope on Earth was able to see against the blinding light, was an asteroid big enough to destroy an entire city. From behind the sun, asteroid 2002 MN came hurtling towards Earth, faster than a speeding bullet. It shot past, less than a third the distance to the moon, and nobody saw it, until 3 days later, when the rock emerged from Earth's shadow into the night sky, going away.
It looks like the Earth just dodged a bullet. Actually, it was an asteroid. Scientists say it blew by last week at a distance they describe as a close shave.
The airline industry would call this a near miss. Scientists who study asteroids and comets called it a problem.
The threat of asteroid impacts on the Earth is very real. We know that throughout history this has happened. The craters we see on the moon are examples of the kind of impact history that the Earth has had. But it also happens very rarely. So it's a very unusual kind of hazard. It's a hazard in which the risk in any one year is very low, but it does happen, and if it really did come about on our watch, it could end civilization.
These cosmic bullets originate on the far side of Mars, in the main asteroid belt, where a bracelet of celestial debris circles the sun. Millions of rocky fragments, building blocks of a planet that never quite came together when the solar system was formed. What's often depicted as a busy cosmic junkyard is actually more like a big empty speedway. The rocks are far apart and moving very fast, ranging in size from pebbles to boulders to rocks the size of Mount Everest. Occasionally, the tug of Jupiter's enormous gravity drags an asteroid off course, causing it to crash into another asteroid. Some veer away into new orbits that cross the paths of Mars, Earth, Venus or Mercury. Another ring of debris called the Oort cloud is the source of most comets, which are big, rocky ice balls that orbit the sun and cross the paths of the inner planets. All the inner planets and our moon bear the scars of numerous asteroid and comet impacts.
We do get hit all the time by pieces of debris from asteroids and comets. In fact, 40,000 tons of cosmic debris plummets into the atmosphere every year. We see them every night as shooting stars. They don't hit the Earth very often, but when they do, clearly it isn't just going to be a matter of a shooting star seen in the sky. So it is inevitable. It's only a matter of time before the next big one hits us.
Even small rocks can make a big impression. In 1908, about 2,000 square kilometers of Siberian forest were instantly flattened as an asteroid exploded near the Tunguska River. The impact site was so remote, researchers had to mount a wilderness expedition just to find the place. When they arrived, there was no crater. Paintings, based on eyewitness accounts, described a fireball. A horrendous explosion in the sky.
Didn't actually come crashing down to the ground. It exploded maybe 5 to 10 kilometers up in the atmosphere, and that made a big blast wave in the atmosphere, and that is what did the damage.
All this was caused by a relatively small asteroid, somewhere between 50 and 100 meters across. Roughly the same size as asteroid 2002 MN, the one we couldn't see coming. Tunguska's 2,000 square kilometer blast wave would have leveled London. But as bleak as the thought of cosmic collision may be, there is at least a glimmer of hope.
One of the special things about the asteroid impact problem is that unlike the weather or earthquakes or other natural hazards, we, at least in principle, we could do something about it.
And when we know one's coming for us, our claim is that the technology is available today to stop it.
On the Earth, we've got active geology, we've got volcanoes, we've got earthquakes, we've got continental drift, we've got rain, we've got wind, we've got storms, we've got snow. All of those things erode away craters, and that, in some ways, actually fools us into thinking that indeed the Earth doesn't get hit as often as it actually does.
Counting craters on the Moon and then estimating how often the Earth gets hit can be a pretty sobering exercise. One scientist who made that kind of calculation was astronomer Ernst Opic, who published his impact estimate back in 1951. The general public, however, paid little attention to the science or the implications. But one individual who did take the issue to heart was Lembit Opic, the astronomer's grandson, who got himself elected to Parliament.
My grandfather is the reason why I carried on in politics, what he initiated in science. In essence, he was a pioneer. He saw the danger of asteroid and cometary impacts with the Earth, and he had the courage to speak up about them. And he did that at a time when it wasn't really taken seriously, in the 1950s and 1960s.
After years of pushing and prodding, Lembit Opic convinced the British government to commission a comprehensive scientific study of the asteroid and comet threat. The expert conclusion was, the threat is indeed real.
Now, the government has set up a task force to examine the risk of an asteroid hitting the Earth.
Still, skeptical politicians might want to get on the bus and take a trip to the Natural History Museum. Ask any schoolchild who's been there recently, and you'll hear a fascinating and truly scary tale about what happened to the dinosaurs.
The dinosaurs were alive here. They were dead when this sediment was deposited, and this layer is one of the most unique layers in Earth history.
In 1980, the discovery of iridium beside a layer of clay which marked the end of the age of dinosaurs led Lewis and Walter Alvarez to publish a theory that a huge asteroid or comet had hit the Earth 65 million years ago and wiped out the dinosaurs. But for this concept to be confirmed, there had to be a crater. There may be tons of dinosaur bones in these dry canyons, but where on earth was the big crater? Just the kind of mystery a budding young scientist would love to solve.
When I went back to...
Off the coast of Mexico's Yucatan Peninsula, Dr. Alan Hildebrand investigated a huge gravity anomaly discovered by oil drillers back in the 1950s. Put that together with a semicircular magnetic anomaly and you get a massive crater, 180 kilometers across, near a little village called Chicxulub Pueblo. Most of the crater is underwater now. Erosion and continental drift have covered the visible evidence. But 65 million years ago, this was ground zero.
This object would have fallen through the atmosphere in just a few seconds. It's going through the sky, it would have been brighter than the sun. As soon as it contacts the surface of the shallow sea in Chicxulub, of course, it starts propagating the shock wave down into the planet, and it keeps pushing into the planet, and it only gets stopped maybe about 30 kilometers down. The pressure wave would have traveled around the entire planet in the atmosphere. You could have heard the impact on the other side of the planet. The giant impact fireball rising out of the hole, it would have risen, say, 10,000 kilometers above the surface of the planet. Near the impact site, it would have been so hot, it would have evaporated the clouds and been hot enough to make the forest, even a green forest, begin to burn.
For Alan Hildebrand, finding that crater pretty much clinched the argument. Planet Earth had been all but sterilized by a rock the size of Mount Everest.
3/4 of the species of large animal life went extinct.
We have made the case. We've got the qualitative information and we've got the statistics to show that there is a very serious risk.
If you wanted to save planet Earth from cosmic disaster, where would you find people with all the right stuff to do the job? Well, Houston, Texas might be a good place to start looking. This town has that rarest of breeds, the space cowboy. Houston is home to NASA's Johnson Space Center, where rocket science is a way of life and astronauts learn their trade.
If you could roll me 90 and then go down, I'll come in on my side.
Behind a swimming pool big enough to swallow an apartment block, you'll find a small research lab where the rocket engine of the future is being built and bench tested.
Yeah. Very nice. Question is, how big is the plasma going to go from here to here?
Dr. Franklin Chang Diaz is one of the lead researchers, as well as an astronaut with 7 shuttle missions under his belt.
And in fact, there was a time in one of my flights where we got hit by very tiny micro meteorites, perhaps, or some sort of orbital debris, which made little tiny dents or little craters in the windows of the shuttle.
Well, that tube is welded. Yeah, I did it. You already welded it. Yeah, I did it.
First-hand experience with rocks in space gave birth to a new idea and a dual purpose to Chang Diaz's work here. His rocket engine has been developed for long-distance missions to Mars, or as far away as the icy moons of Jupiter. But it could also be used to push a dangerous asteroid out of harm's way.
I am concerned enough to think that we need to not waste time arguing about it as to whether it's real or not. I think we need to move ahead and do them.
Well, I'm wild and the hell's free. Come on, baby, you belong to me. Sweet kiss makes my passion start. Well, I'm wild and the hell's free. Come on, baby, you belong to me. Sweet kiss makes my engine start. The way you move, you own my heart. Sweet kiss makes my engine start. The way you move, you own my heart.
if this is a threat which has a very low probability, all it takes is one, and we are history.
But before we can send a spacecraft chasing after a rogue asteroid, we have to know where to look for it. In the American West, if you drive across the desert to the White Sands Missile Range in southern New Mexico, you'll find the most powerful and effective asteroid hunter on Earth. Scientists here have tested everything from rockets to the very first atomic bomb. Today, across the valley floor from the Trinity bomb site, the US Air Force has installed one of the world's most advanced telescopes. This state-of-the-art technology was developed by MIT's Lincoln Laboratory as part of the Star Wars anti-missile defense system. These may not be the world's biggest telescopes, but they clearly are the best when it comes to finding deadly rocks in space. This is LINEAR, the Lincoln Near-Earth Asteroid Research Facility.
On a given night, when we scan the sky with this, we'll find perhaps 10 to 12,000 moving objects in the sky. Now, most of those are main belt asteroids, and as such don't represent any danger to Earth. But on the other hand, something like half of those will be brand new discoveries, and buried in there will be 1 or 2 near-Earth objects.
Because the Earth rotates, the sky is always moving overhead. To get a clear picture of an asteroid, you have to make the sky stop moving. And you do that with a telescope that can track or follow the stars. This way, you can take time-lapse pictures that isolate the blur of fast-moving asteroids against a crystal-clear sky. It then records these pictures like a TV camera on a computer chip that has 20 times more detail than the picture you're now watching. The linear computer deletes previously known stars and planets, leaving a less cluttered time-lapse sequence of the new discoveries. At the end of each night shift, Linear's thousands of new discoveries are emailed to the International Astronomical Union's Minor Planet Center at Harvard University. A team of only 3 scientists must cope with the avalanche of new sightings, searching for potentially hazardous asteroids or comets. Computers make a rough calculation of an asteroid's orbit, but it's up to Brian Marsden to estimate the level of risk.
They may be reporting 50 or 60,000 observations from one night, and it takes a while to get through that. But so we look first at the fast movers and see if there's anything interesting there. H is equal to sine delta.
We do sometimes get close to 70 or 80,000 observations a day, almost 1 per second. There are some days when we effectively have 1 observation per second.
Even with fast computers, Marsden's team can make only a preliminary calculation of each asteroid's orbit. 5 shots in one night cover only a tiny segment of an asteroid's orbital path.
You can't solve for the orbit completely from that, but the fact that you're seeing motion over a half an hour or an hour, something like that, does allow us to get a partial solution for the orbit.
Refining the orbit gets complicated. When 2002 MN shot past, its trajectory was warped by Earth gravity, and scientists at NASA's Jet Propulsion Laboratory in Pasadena, California, had to add that to their calculations.
Here's an animation I put together of the asteroid last year, which was discovered after it passed by the Earth.
An elite team of mathematicians and celestial mechanics is now working full-time on a computerized warning system.
Our orbit animation, you can see how when it returns out to the asteroid belt, the close approach to the Earth has changed its orbit, and it's no longer returning to the same place it started.
Because 2002 MN will circle around the Sun and come past us again, the NASA Orbital Mechanics team will have to adjust the calculation in order to know whether it will ever pose a danger to Earth at some point in the future.
So here we've zoomed in on the Earth-Moon system and we're looking down. You can see how close it came to the Earth that went over the top, and how you can actually even see the bend in the trajectory. So it's a great example of how a close approach to the Earth, or in fact any planet, can be used to, or can change, significantly change in orbit.
To know where an asteroid is likely to be in the future, you need a model of the solar system. Mechanical models that show the relative motions of the Sun and planets have been around since the early 18th century. They're called orreries. What the celestial mechanics at NASA had to do was create a new digital model. One that includes the gravitational attractions of all the planets and the Sun, and all the other forces that can affect where an asteroid might go.
You just compute what forces are acting on this particular asteroid from all the planets and many of the minor planets in the solar system, and then we can actually trace the motion of that object around the solar system for hundreds of years.
For scientists, the acid test of their mathematics came when a strange new comet raced toward Jupiter. A stream of cosmic bullets that would shock and amaze millions here on Earth. In the spring of 1993, the eyes of the world turned almost in unison towards a doomsday rock like no other. From the far side of the solar system, it flew in a death spiral toward the largest planet. Gene Schumacher, his wife Carolyn, and their colleague David Levy had discovered an odd-looking streak of light that turned out to be a fractured comet. 21 large chunks of icy rock and cosmic dust heading towards Jupiter.
We knew we had something very unusual. It was so unusual we were a little unsure just what we were dealing with.
NASA asked Paul Chodas and his team to calculate the orbit and predict whether this new comet would actually hit Jupiter.
And it started off at some 60%, and before long it was 90%, and this was a year before impacts. As the impacts approached, we continued to predict not just the impact probability, which went very high, but where and when the comet fragments would hit the planet. And it was a prediction months in advance, and as we got closer and closer to the impacts, I kept wondering, well, is the math right? Will this actually happen the way it was predicted?
A giant comet is on a collision course with Jupiter.
Everybody on Earth who was paying any attention wanted to see if the comet would actually hit Jupiter.
We have liftoff of the Space Shuttle Endeavour on an ambitious mission to service the Hubble Space Telescope.
NASA's Hubble Space Telescope set its sights on the planet, and the pictures of what happened next were truly stunning.
Right there! Get it! Wait.
And then the impacts occurred. We were within minutes of getting the right answer on the time of impact, and the location of impact turned out to be just right.
Over the next week, 20 more fragments of the comet crashed into Jupiter, some leaving scars as large as the Earth.
Bang on its cosmic schedule, the comet's first impact was recorded by NASA within the last hour.
When fragment G slammed into Jupiter, releasing an amount of energy equivalent to about 6 million megatons of TNT.
In the wake of SL9, a group of concerned scientists gathered in Italy for a brainstorming session. They created a brand new international organization called the Space Guard Foundation.
Okay, I'm going to join.
To promote the discovery and study of near-Earth objects.
Some people imagine that there are lots of astronomers out there scanning the sky looking for incoming comets and asteroids, and that, of course, is not true. In fact, until recently, there was hardly anyone out there looking.
It's going to glow for about a half an hour and set everything on fire around you.
But whose job is it to defend planet Earth? Weapons scientists from the United States and Russia had already held a series of meetings and came up with their own ideas about how to deal with the impact threat.
Blow off some material, you get a reaction in this perpendicular direction.
The military establishment under Star Wars had created a whole lot of devices, or at least concepts, for weapons in space and devices in space. And in the early 90s, when the Star Wars program was looking a little bit iffy, I think there was some motivation for them to try to apply their technology to this newly discovered hazard from asteroids and comets.
The military approach to the problem proved to be controversial. The notion of sending nuclear weapons into space generated an immediate backlash.
Edward Teller was proposing that we blow up an asteroid to show that we could protect the Earth, and I thought that was a pretty crazy idea. Blowing up an asteroid with a big bomb has a lot of problems associated with it, violating treaties, taking a single asteroid and making a swarm of smaller asteroids. It seemed like it was more of an interest in bombs than it was a serious interest in defending the planet. For NASA, on the other hand, NASA obviously is the natural agency to discover the threat and the objects, but they say no, planetary defense, that's a military obligation and not an obligation of NASA.
Not NASA, not the military. Just when it seemed planetary defense was nobody's job, a tiny speck in the sky would set off doomsday alarms around the world. On a winter's night, the 6th of December 1997, a dim streak of light moving through the constellation Cancer was captured by a telescope in the Arizona desert. Big enough to destroy civilization as we know it, asteroid 1997 XF11 seemed to be heading towards Earth. The initial sighting by the Kitt Peak Observatory in Tucson, Arizona, was relayed to the Minor Planet Center at Harvard University in Cambridge, where a computer made the first rough calculation of the orbit. They were pretty sure it would miss the Earth on this pass, but it would be coming round again, and it looked like there could be a problem in 30 years.
There were indications of close approach to the Earth in 2028. That was about 45,000 kilometers, which really was rather close.
With only a handful of sightings, the orbit calculation remained very rough. It was hard to tell where this rock was going. So Brian Marsden posted a bulletin asking astronomers around the world for more observations before the rock became too faint to see.
I was saying, hey, get your big telescopes onto this. On the one hand, we're only going to be able to observe it for another month or so. We want to improve the orbit calculation and find out exactly how close it is coming.
But one line in the bulletin said that the chance of a collision was small, but it was not entirely out of the question. Within hours of the website posting, reporters discovered XF11, and doomsday headlines screamed around the world. Because the close approach in 2028 would put the asteroid nearest to Europe, London newspapers focused on the exact moment life on Earth might possibly end.
Pictures of it on the internet show it as a tiny moving blob. Scientists have calculated its path in the year 2028.
Watch very carefully. September, October the 28th, the two coalesce.
But at NASA's Jet Propulsion Laboratory in California, The orbital dynamics team thought there must be some mistake.
To my great surprise, when we ran our software, it said that the probability of impact of this particular asteroid in 30 years was essentially 0.
As it turned out, the end-of-the-world asteroid would miss the Earth. That big rock in space posed no threat after all. A frantic hunt through the archives at NASA had turned up photographs of XF-11 taken 8 years earlier.
And as soon as those were placed into the orbit determination process, they confirmed the fact that there was no chance that it could hit the Earth in 30 years.
The public at large was not understanding uncertainty in this. They wanted an immediate answer. Is it going to hit us or not?
But people were paying attention. One side effect of the false alarm was that public and political awareness of the threat had been raised. 2 months after XF-11, new hearings were held in Washington and NASA was told to speed up the science of asteroid detection. Finally, it seemed, there was a political will to do something. Congress gave NASA a 10-year deadline to search the skies and get a fix on the largest of the doomsday rocks. They called it the Space Guard Survey. While astronomers geared up to search the skies, Hollywood was going into overdrive.
I would go to every dinner party and I would say, are you aware what would happen if a comet was actually on a collision course with the Earth?
Oscar-winning screenwriter Bruce Joel Rubin was hard at work on the remake of a sci-fi classic. The new film, called Deep Impact, would be a Steven Spielberg production.
When we arrived at our hotel in New York, the porter was so incredibly careless with our bags. And the room they gave us, it was beautiful. A broom closet. But the worst part was the shower. My wife drying herself with the
Egyptian cotton towels.
Shower curtain defined that whole vacation for her. Don't just visit New York.
Visit TripAdvisor New York.
With millions of reviews, a visit to TripAdvisor makes any destination better.
An army of scientists work desperately to build this giant rocket, this modern Noah's Ark, to carry a few picked survivors of our doomed civilization.
I think the thing that was hardest for me was the realization that people would have to be chosen to survive.
Let's take the ship away from them! Come on!
Probably a very, very small percentage of human beings would be left on the Earth able to survive something of the intensity of the comet that hit and destroyed the dinosaurs. So I felt making this movie is not just a mission to tell a good story, it's to change minds. It's to let people go, this is something real. This can happen to us. This movie is a wake-up call. It's not just a Hollywood movie, it is pointing at you.
As Hollywood released Deep Impact, telling the world in no uncertain terms that cosmic collisions were no longer just a cosmic joke, real-life professional asteroid hunters were making movies of their own. But instead of using cameras, they worked with delayed Doppler radar. Take the same technology behind a police radar system, jump the power to 400,000 watts, and you've got NASA's Deep Space Network, with huge multi-dish systems, like the Goldstone tracking station in California's Mojave Desert.
This is the main room of the pedestal of DSS-14.
The first time radar astronomer Stephen Ostro bounced a signal off a rock in space, a wobbling blot of pixelated data bounced back. What looks like digital gibberish spoke volumes to Steve Ostro.
Radar really does three things at once. One, it works at long wavelengths, so you're sensitive to structure on large scales and metal concentration. The other is you can make pictures. And you can't do this from the ground in any other way. You make pictures of objects, and then we take a sequence of pictures, and we go through a computational process to produce the 3D models. That's the second thing. The third thing is that it makes very precise measurements of distance and speed.
When the 1,000-foot radar dish at Arecibo in Puerto Rico bounced a beam off an asteroid called Castalia, the data was translated into a 3D computer model. The very first radar movie showed how Castalia spins and revealed that it was actually two massive chunks of rock held together by weak gravity. Every time they made the trip to Goldstone for a new radar target, Ostro and his team were like kids reaching into a box of chocolates. They never really knew just what they would find. Asteroid Cleopatra, shaped like a dog bone, was roughly the same size as the state of New Jersey and was made almost entirely of metal. Echoes from asteroid Tutatis produced images of a rocky, cratered surface and a wobbling, tumbling spin.
Every single one of these objects that we've made a shape model of is very different. This is Tutatis.
From a telescopic smudge of light to a 3D shape model, radar gave them physical details and the first clear idea of what asteroids are really like. In the year 2000, the radar movie crew developed a dark and mysterious new image, asteroid 1950 DA, a big rock that gave everybody a bit of a shock.
Once we got the radar data, we began the normal process of just seeing how far in the future we could predict this thing before the uncertainties in the orbit blur out. And in this case, we could go over 880 years into the future. And what was startling about that case was the impact probability turned out to be non-zero.
Non-zero means there is a chance this rock could hit us. On March the 16th, in the year 2880, 1950 DA will cross the Earth's orbit. Will it hit us? The odds, 1 in 300. If 1950 DA does hit the Earth, the most likely point of impact would be at sea. Of all the big asteroids discovered thus far, this is the most dangerous one we know. Eric Asfaug and Stephen Ward have created a computer model of the impact.
Yeah, it's kind of funny how this started. It was with the movie Deep Impact, and I was getting phone calls. Lots of people were getting phone calls about the movie, whether it was accurate, the big cresting tsunami coming across.
The concept here is that this asteroid, which is about 1 kilometer across, will hit the ocean at 17,000 miles per hour, and it'll blow a hole in the ocean about 19 kilometers across and all the way to the bottom. And so when this huge hole of water gets blown into the ocean, the water will run back in again, and it overshoots and it collapses and overshoots many, many times, and each time it pumps out a wave. So it starts out hundreds of meters high, comes ashore on the coast of North America at about 50, 60 meters, up toward Canada, Grand Banks, it's about 40 meters, 20 meters here in the coast of South America, and about 15, 20 meters all the way over to Europe. These waves would run inland about 4 kilometers, so pretty much everything within 4 kilometers from the beach would be covered up repeatedly. And so we'd pretty much be wiped away like you're scrubbing the floor. You know, just scrub like this, and it's pretty much we'd all be carried back out.
In February 2001, a NASA spacecraft called Near Schumacher made the first ever landing on a chunky, pockmarked rock named after the Greek god of love. Asteroid 433 Eros is 33 kilometers long and 13 kilometers wide, one of the largest near-Earth asteroids. The pictures were spectacular. The data will take years to process. Proving that they could land on an asteroid was a major achievement, but in the end, they still don't know much about what's inside. How dense? How tough? How brittle or crumbly is it? What would happen if they gave it a good shove? The surface appearance of any dark and mysterious object can be very deceiving.
So these two spheres, as far as I can tell, have exactly the same mass, the same compressibility, the same color. If I were a spacecraft orbiting these and these were asteroids, I'd be very hard-pressed to tell which was which. Yet, if I dropped them from a height, and only one of them bounces, really illustrates the fact that one of these responds elastically and one of these responds like a lump of clay. And it's critical to really go and find out what's inside before we even start thinking about moving these things around.
When a 3D model of the asteroid Castellier got smacked in a computer simulation, a problem occurred. An impact with the same energy as the Hiroshima bomb turned Castellier into a pile of rubble, but did not deflect its trajectory in any significant way. But there are other ways to apply force to deflecting an incoming asteroid. Using the power of the sun to push dangerous rocks out of the way may not be so far-fetched after all.
This is a typical near-Earth asteroid. Its name is Galevka. It's about half a kilometer across. It's a hazardous asteroid. Its most likely fate is going to be to strike the Earth someday, thousands of years from now.
Modern-day researchers like Eric Asfaug say the idea of a giant orbital magnifying glass to burn space rocks could work.
You create a vapor plume in one direction, and that starts the asteroid moving in the other. It's a very gradual process. It's not going to happen instantaneously. You need to know where this guy is 100 years or 50 years ahead of time. But if you do, you've got all the time in the world for a satellite to sit there, no human intervention whatsoever, and it'll gradually shove the asteroid into a different orbit, and it'll miss the Earth.
Some of the technology to do this already exists. Take an inflatable parabolic antenna the size of a tennis court, convert it to a solar collector, and use it to focus sunlight on an asteroid. The Russians have built and are testing a giant sail that captures the minute pressure of sunlight. Just attach the sail to an asteroid and let the rock hitch a ride to someplace else. But using the sun to save the Earth means waiting for nature to do the work. If we don't see an asteroid until the last minute, solar power would be too little, too late. A nuclear electric plasma engine could push an asteroid out of harm's way. The rocket technology at this NASA lab in Houston, Texas, could provide the power for a space tugboat. A group of astronauts and aerospace engineers is designing the B612 mission to prove that asteroid deflection can be done with existing technology.
These are rockets that have very tiny amounts of thrust, but they are so frugal in the use of propellant that we can keep the rocket going for periods of the order of a year.
Building a better rocket engine is only the first step. Figuring out how to latch on to an asteroid, point it in the right direction, and push without losing control is the really tricky part. After years of research, NASA finally had it, the first complete draft of a plan, a demonstration mission, to save the planet.
We can move the asteroid off the impact with the Earth 10 years later so that it misses the Earth, and not just miss it randomly, but miss it very precisely so that we don't simply pass on the problem to our grandchildren.
Midway through 2003, the Space Guard survey had reached the halfway point. A little more than half of the kilometer-sized near-Earth asteroids had been located, and the news was mostly good.
For the 60% that we have already found, I can tell you that there is not a single one that poses a danger. For the 40% that we have not yet found, I can tell you nothing. One could hit tomorrow. Not very likely, but until we've found them and cataloged them, we won't know.
But finding the really big asteroids, those 1 kilometer monster rocks capable of ending human civilization, is only the first part of the challenge. There are an estimated 50,000 smaller asteroids that are big enough to cause tidal waves or destroy vast regions of the Earth.
A 200-meter asteroid happens maybe once every 10,000 years, but that's like 600 megatons to 800 megatons exploding in one place.
Recall the small 60-meter rock that exploded over Siberia in 1908? Well, even though it could have destroyed a city like London or New York, rocks that small are not included in the current Space Guard survey, meaning no one is officially looking for them.
Which, of course, is the same thing as saying that chances are enormous that a Tunguska-sized object will find us before we even see it coming, as happened in 1908. That is likely to happen nowadays, that we won't see it coming.
There has been talk of expanding the search to include smaller asteroids. It'll take more and bigger telescopes and, of course, more money. But until we do, we'll have no idea where those city-killer rocks are.
Evolution on Earth has proceeded in part because every so often a global catastrophe comes along, pushes the reset button, and new things happen.
It wiped out the dinosaurs 65 million years ago, and at the time, we mammals were just furry little creatures burrowing around in the ground, and an asteroid or a comet impact took out our principal competition.
I guess we are saying implicitly, if not explicitly, that we want to do away with that natural cycle.
We've had enough evolution. We like ourselves on the top of the ladder. And we can do something which will change cosmic evolution from this point forward in terms of life on Earth.
Dinosaurs ruled the Earth until a big rock wiped them out. The question is, will another rock do the same to humanity?
Let's get a couple good pictures here.
Humans are the first species with the potential to block a doomsday rock and switch off the evolutionary reset button.
People very often say, look, you're just a doomsayer. You think that these awful things are going to happen. I'm not that way at all. I'm entirely optimistic. The way in which I view asteroids and comets and the possibility of them hitting the Earth is that it's a great challenge. Thank goodness we've realized the hazard and the danger before the next one happens. It's given us time, we hope, to do something about it.
Scientists can study the sky and find the dangerous rocks ahead of time. Astronomers can do the math and predict the orbits. People have the desire and the right stuff to do the job. There's a whole new field of science that could give humanity an option the dinosaurs never had.
Left-hand downwind runway 22, the QNH and the QFE 1012.
I love the North Wales coast. Just look at that view. I grew up in Prestatyn, and I used to sunbathe on that beach down there and look up and see the aeroplanes coming in and out of Liverpool Airport and think, one day I want to fly a plane. It's taken me a long time to get there, but now here I am. Hello, Prestatyn.
All that I want is a pair of wings to fly.
On radar, November 242 Charlie Victor. We are 11 miles to the northwest. Request joint instructions.
I've recently qualified as a pilot, fulfilling my childhood dream. And this is the first time I've ever flown low over my home patch.
What I didn't realise when I was growing up is that North Wales is one of the hubs in the world for aeronautical engineering. And down there is where they build some of the best parts of aircraft in the world.
Airbus Broughton is located on a massive 750-acre site in Flintshire. Here they build wings and then transport them on this extraordinary plane to the south of France. Everything they do is on a gigantic scale. And their latest groundbreaking design is taking the aeronautical world by storm. My little plane isn't as big, but she's just as loved.
November 2 Charlie Victor, runway 22.
I'm flying in to find out how these brand new wings are setting a new benchmark standard for fuel efficiency.
You're parking on apron Bravo with the Beluga. So once runway vacated at Bravo, if you follow the marshal's instructions.
It's cutting-edge stuff. We may never fly in the same way again, and it could all be down to some Welsh wings. Broughton is famous for building wings. The wings of an aeroplane are critical to how the plane flies, its handling and its fuel efficiency. And this year they're celebrating 75 years since production first began on this site. Today they're supplying some of the most popular airlines in the world, and that keeps around 6,000 Welsh workers busy. And I get to join them. So you're the man in charge here.
Yeah, it's good to see you here. Welcome to Broughton. This is where we build A350 wings. The A350 is one of the most advanced aircraft in the world. It's made of advanced materials. 70% of the product is advanced materials, and 53% of that is carbon fibre composite.
Carbon fibre is a form of soft graphite, just like what's found in the centre of a pencil. It's mixed with plastic resin to make carbon fibre composite. It's tough, lightweight, but extremely flexible.
We're currently building 1 pair, 2 pairs per month, but by the end of this year we've got to get to 5 pairs per month.
Within a year?
That's a 5 times increase, that's correct. I understand you know a little bit about engineering, Carol.
Compared to you, about that much.
Would you like to join us?
I'd love it. I really would love it.
OK, great.
The moment has come for me to get hands-on experience in building one of these wings. This uniform reminds me of when I was a very junior engineer at the Dinorwick Power Station in Snowdonia. And of course we had the capped shoes or boots, the boiler suit or overalls, and the obligatory hard hat. Yes, sir. They call this the washing line, and you can see why. Except here, we don't have clothes hanging down. We have the skins or the covers of the wings. This is the top cover, and this one here is the much more curvy bottom skin. What's so remarkable about these is that they are the largest single pieces of carbon fibre composite ever made in the world. And that gives you some indication of just how revolutionary this place is.
Good afternoon, Station 82. So to start with, safety, okay, no near misses, no accidents.
It's the start of shift, and we're all lined up for the team briefing.
Some of us will be supporting MSN 25, removal from jig. Any issues? Right, thank you very much, guys. Have a nice afternoon.
My first job is to move this 2.5-ton carbon fibre top skin of the wing into the jig so we can work on it. To manoeuvre it around the factory, we're using a special vehicle known as the AGV.
Hi, Carol.
Hi,
your turn to shine today.
All right, then.
You going to help us out?
Yeah,
moving
moving the cover.
Going to move the cover today?
Is that for me?
Yep.
Hope it's the right size. I have got my certificate in
Good.
forklift truck driving. It's
Well,
not quite the
that's
same,
not
is
going to
it?
help us today.
So put this around my waist.
This is the
or-
box. This is the dead arm box.
What does that mean?
My colleague's going to be driving.
What's a dead arm box then?
If there's a problem and we're
Yeah.
swinging and we're coming to a bollard, if you think it's unsafe,
Yeah.
take your hand off that,
Yeah.
and the machine, AGV will
Just
stop,
cuts out.
cut out straight away.
And that's worth millions, isn't it?
I'd have guessed, I think possibly 1.1 million, too.
Yeah.
So,
1, 2.
that's only.
It's only
It's
carbon
only money,
fibre,
isn't
eh?
it?
It's only money.
So, Eddie, good to go.
Right, I'm sticking with you, Russ.
Yeah.
This is brilliant. The way this
And
moves.
It's fantastic.
These wheels are incredible.
And I think it's roughly about £8,000 a wheel.
Is it really?
Yeah.
This is an extremely delicate manoeuvre, and you can feel the pressure. The team knows that one false move could cost a fortune.
Take your hand off now, you stop straight away. It's looking like possibly may have to move this frame.
This AGV not only manoeuvres, but it can also lift this heavy and expensive piece of wing.
You're going over the top?
First flight.
First flight, yeah.
Luckily, it has just enough reach to clear the frame.
It was designed by the Americans, is that right?
I think that's German. Kuka, I think Kuka's
Say that again, what was it?
German. Stan Gordon.
I know, yeah.
The next stage in the manoeuvre is to lift this delicate topskin right up to the ceiling of the hangar and then across to the jig. The frame uses 103 vacuum suckers, just like the suckers to hold your cuddly toy in the car, but just a little bit more powerful.
I feel as though I'm attached to this wing now. Some kind of ethereal way.
Come on, Carol, give it a full whack.
Bit of welly.
Yeah, give it a bit
go,
of welly.
Baby, go! Woo. She doesn't swing as fast then, does she? She's good.
The quicker it's in the air, it's safer.
But she's safe, tidy up
She's
there.
safe, she's not swinging, and she's happy to be drove in now, no problems. So I want to take it into the jig now.
Yeah, go on.
And then we're going to lock it down.
All right, I'll hold the paper.
Thank you.
While I leave Rossi with the tricky job of positioning the topskin, I'm going underneath to get my hands dirty and come face to face with those carbon fibre wings.
All right, boss, what we're going to do?
Basically, the machine comes in, drills all the level cover, but it can't get in this area because it clashes with the cantilever.
The pressure is on me now to drill the perfect hole. The drill I'm using here is powerful, and to stop costly mistakes, it's completely automatic. Perfect. One down. Several thousand to go. Although I've got a sneaky feeling that someone's drilled some already.
That's it. Good hole.
Thank you very much.
Choosing carbon fibre composite over old-fashioned aluminium has meant huge changes for the workers here.
I mean, the thing is, for someone who's a passenger, what it's made of is so completely different, isn't it? The kind of the cleverness is hidden almost. From a passenger's eye.
It's just metal. We've worked with metal for so long, and now it's all of a sudden it's just it's different.
Like NASA.
It was like going from
NASA.
It's like going from the cave to NASA.
It was.
We're like cavemen. Cavemen to astronauts in a week.
Failure is not an option.
Working with carbon fibre has completely changed how the wing can be shaped. The curve in this panel could mean cheaper fares for everyone, as it reduces fuel burn by 25%. To understand how, I'm going back to the basics of flight.
It's the wing that gives us lift. Now, I'm going to show you just with a little drawing about how it works. So I'm going to draw my wing here, and generally on a wing, the curvature on the top of the wing is greater than on the bottom, and there's a reason for that. So this is my airflow. So when a wing is moving through the air, you see that a dot on this bit of air coming over has to go all the way over the top of the wing. Similar dot just travels underneath, and then they meet up at the back and then on they go. Now, the thing is, when this one going over the top of the wing travels, it has to go faster than the bit of air on the bottom. So what you get is you have high pressure on the bottom, low static pressure on the top, and the high pressure pushes the wing upwards, and that is the force that we call lift. Or, when you're looking at an aeroplane, I call it magic.
It doesn't matter if it's a jumbo jet or a bumblebee. They each achieve lift in the same way.
Now, if you don't believe me, you can do this at home. Get a bit of paper, okay, static pressure the same, the weight of the paper is hanging down. When I blow across the top, the pressure on the top will reduce and we will have lift
You see? But once in the air, the shape of the wing determines the way the aeroplane flies. The best way to demonstrate is with a bit of aeronautical origami.
I think you're a bit of a neater folder than me.
Oh, is that what it is? You're after speed. And as a former fighter aircraft designer, Roy Scott knows all about it.
One of the main principles is the angle of the wing relative to the fuselage, the body. So, for example, here, what we're looking for is a very stable flight on a passenger aircraft. What we do is slightly fold the wings upwards to give that upwards effect, and that's called a dihedral wing
Dihedral
effect.
P-wings.
Yeah. And the Harrier jump jet, for example, where we want an unstable aircraft because it can roll
You
fast.
worked on that as well.
That's correct, yes, down in Farnborough. The wings are formed downwards in an anhedral effect.
So if you look at fighter aircraft, you can see that.
Yeah.
Okay.
So mine, theoretically, should go the furthest.
And mine should do the rolling, spinning and all of that.
Okay.
3, 2, 1.
Yes!
So yours was spinning quite a bit.
Yeah.
Mine somehow nosedived. So maybe with a secret paper clip in there.
Yeah, that's what it was. Airbus is one of the biggest employers in Wales. Building wings keeps a workforce of over 6,000 busy. There are currently only a few completed A350s in service, but the pressure is on to supply 780 pairs of wings on order to customers such as Qatar Airways. But this factory has a long history of working against the clock.
This is a bomber factory in Britain. The workers have arranged with their management and their joint production committee to build a bomber in the record time of 30 hours. The clock strikes
This is
9
Broughton
and
back
the
in
record-breaking
1943.
attempt begins. 2 sections of the fuselage.
Here, a team from the factory are attempting to set a world record to build a whole Wellington bomber aeroplane.
You can get some idea now of the size of the bomber. It's almost 65 feet long.
During the Second World War, while the men were fighting on the front line, women were clocking into factories all over Britain to help in the war effort.
The progress they are making speaks for itself. For it's only 10 o'clock, 1 hour from the starting time.
Betty Weaver was one of the women trying to smash that world record. She was recruited to work here from the local co-op. She's 94 now.
The first day I turned up, there was 2 of us together. We had our photograph taken to put on a pass. I was under the largest white boiler suit I've ever seen in my life, and a wooden box with tools in it. And I didn't know which one to use or which end to start, but I was thoroughly taught for about 3 weeks.
Yeah.
And that was it. I was on my own.
So here was this massive production line, and little Betty...
Big Betty.
So which job were you given then, and the whole construction? What was your job on it?
Well, it was the intercom inside the plane, where the crew kept in touch with each other.
Okay.
2 ladies before me used to run the cable through the plane.
Yeah.
And there was a box of fare at each station,
Yeah.
so that the pilot could keep in touch with all his rail gunner, the navigator, the wireless operator, second pilot, and I connected the boxes up.
And did that remain your job through
Yes,
the war then?
all the way through.
So everybody specialised in one
Exactly,
thing?
yeah.
Because the wings and the fuselage were fabric, weren't they?
Basically, yes.
The cover of them
Yes.
was fabric.
Yeah, it was linen that they stitched on.
Yeah.
And they had to do 12 stitches to an inch.
And that's
if there was 1 stitch missing, it had to be undone and
No.
redone. Yes.
Yeah.
And then it was doped over the top until it was like the skin of a drum, more or less.
Really
that sort of thing.
hard.
Yeah.
And so the inspectors checked all
very
that.
strict.
Yeah.
Very
well,
strict.
It had to be, didn't
Yeah,
it?
exactly.
Men's
Men's lives depending on it.
Absolutely, yeah. Betty and her fellow workers gave up their weekend to try to break that world record.
Here comes the test pilot, Gerald Winnie, a really amazed man. He was planning to fly the bomber this afternoon. But so fast has this aircraft been completed that they got him out of bed to put the bomber through its paces.
It was wartime propaganda at its very best, aimed to bolster spirits at home and put the wind up the enemy. So, did they break the record?
The record? Yes, they broke it, those workers. They said they'd build a bomber in their spare time in 30 hours. Its wheels lifted from the ground in exactly 24 hours and 48 minutes.
And I wonder if that thing got off the ground. I'll never know. I really don't. Yeah. There we are. Yeah.
Broughton has a long history of producing aeroplanes. In 1949, the Hornet took to the skies after de Havilland took over the site. The Heron was built in the 1950s, and the Beaver and the Chipmunk were also built in Broughton. Some aircraft became flying legends, like the Mosquito and the Comet Mark IV. This sleek silver plane was the fastest airliner of its day to cross the Atlantic.
Now then, this is the most modern production area of wings.
Yeah.
So,
And I couldn't let Betty leave without a glimpse of the latest wings.
and look at all of this here. Just go to this barrier. You're right.
Yes. That's wonderful.
That is one big piece of material. It's not put together in any way. It's just made like one piece. And that is the bottom of a wing there.
That's as big as a Wellington bomber would have been.
It is. It is, yeah. But there's no one stitching fabric in here. But
thank goodness. Oh, good job. Unbelievable.
I can't help but be astonished by Betty's story. You can imagine all of those young girls and men learning these incredible new skills in this, strange place, building bomber aircraft at a ridiculous rate. Quite incredible, but, we should all be thankful that they did do it.
Our Welsh wing is beginning to take shape. With the top skin fixed on, it's time for the next phase of work to take place. And how things have changed from when I started out as an engineer. As a woman, I was a rare sight in a male-dominated world. But here at Broughton, I've seen more women engineers at work than ever before. One of them is Bridie Welsh, and she is the expert when it comes to the skeleton of the wing.
Underneath, what you've got here is your spar, made of carbon fibre.
And this goes the whole length of the wing?
The whole length of the wing.
Yeah, to provide stability.
Exactly. And then we've got our ribs in between. Yep. So what's interesting about these is they're made from aluminium instead of carbon fibre because the loads, the forces are quite complicated.
Bridie and her team designed the complex internal structure of the wing. That's because these wings do more than just lift the plane off the ground. They're also the fuel tanks for the aircraft.
Fuel tank starts right at the centre and moves out to around about rib 28.
And how much fuel did the wings take?
It's just under 100,000 litres.
Is it really?
Yeah.
It's massive, isn't it?
It's a lot of fuel.
Yeah. And when the bottom is on, the fuel is actually touching up against this, isn't it? Against this aluminium. So how does that operate? Do you have fuel pumps that take it through?
What we have is baffles. They're little holes within the ribs which allow the fuel to move throughout the rib base.
Without it just being one great big slosh, I suppose.
Yeah.
Right? So, when you go out on the town, do you go into Chester?
I do.
Okay. And the lads chatting you up, beautiful young girl, and they're going, what do you do? And you say, I'm an engineer. What do they say?
They do get a bit of a shock, yeah.
I'm not surprised.
Older commercial aircraft have up to 8 fuel tanks. The A350 only has 3. One tank is under the main body of the aircraft, while the other 2 are in the wings. Between them, they hold enough fuel to fly from London to New York and back again.
Just coming up through an inspection hatch. I'm inside the wing now. The big end, if you like, of the fuel tank. Lots and lots of ribs stretching a long way in that direction. it's remarkable to think that this will be sealed, and the fuel inside here will go through the pumps and so on into the engine, and no one will ever come into here again. So Beth, there are these FOD signs everywhere, foreign object debris, so none of it's allowed through there.
Nothing is allowed into there that isn't already accounted for on our sheets. So I'm going to have to ask you to empty your pockets of any personal belongings, keys, phones, and put them all into this locker here. So anything that we don't
So anyone's
need,
working in this area, they've got to get rid of all this stuff.
Yeah, so anything that we don't need on the aircraft, we decant into what we call our FOD lockers.
Yeah.
Any tooling that is needed, we account for on the sheet, so it's signed in and it's signed back out, and this ensures the security.
Brilliant. Okay, am I allowed to go in like
this?
this?
Yes. So now we can walk into the FOD area. So if I just pass you this way,
right.
So what we're going to do is just clean an area to make sure that the cleanliness.
Okay. So if I wanted to clean under here, I can't actually see that. So
yeah, so this is why we use a mirror, just to make sure that we can get a continued look around all of the products, so you can see every single.
Yeah, I know. It's not like being
angle
at
area.
home, is it? Because you can't sort of, quite restricted in how you can move.
It is. So the mirror is really important to make sure that we don't miss any part of this bay when we're doing an inspection, so you can see every angle.
Yeah. Oh yeah, I can see it's picking up. So how small, because I've got quite a bit there already, how small an object would you be looking for?
So we're looking for the tiniest of fibres. So when we're doing this clean and this inspection, we're looking for any of the residue from the manufacturing processes.
Yeah.
We were also doing trials and tests with our suppliers to get our wipes to be as low linting as possible.
So they don't leave fibres.
So even the wipes that you're cleaning with don't leave fibres.
What are you like when you clean your house?
It's spotless. It's to the same standard.
Right answer.
It's ingrained in you when you've been on the shop floor.
Yeah.
So, after several months in production, the 32-metre wing sits on the factory floor. Tomorrow morning it will leave Wales and head towards the south of France. It's the end of shift, and I've heard from my new buddies there's a celebration around the corner in the social club. From the bygone days of Vickers Armstrong de Havilland and British Aerospace, veterans and ex-workers are getting together to celebrate 75 years of aircraft production at Broughton. I've been invited along, and there's no mistaking the pride still felt by the people here tonight. Everyone, in their own way, loved working here.
We were sheet metal workers, and we were like a big family. Honestly, it was like a big family.
I worked in the plan room, giving all the drawings out to the men when they came.
Members of your family have worked here, too?
Oh yes, my sister, my brother-in-law, my late husband, my son, myself, my daughter-in-law, the whole family.
Everybody. I've been admiring all these black and white photographs that are around.
Which are mine.
Which are yours, I know.
30 years I was in charge.
Were you? Of an archive, was it?
So,
yeah.
it's all I didn't realise you were a North Wales girl.
I'm a North Wales
girl.
Born and bred.
And our Betty's having a lovely time as well. An absolutely beautiful evening, but it's time to go to bed. I've got work again tomorrow. This site never rests. Our wing is preparing to take its first flight. Today it's leaving Broughton and is being transported to Toulouse in the south of France. And it's catching a lift on the strangest looking aeroplane you will ever see.
Beluga, because it's shaped like a whale, a beluga whale. Look at that high forehead. It's like a normal aircraft with this huge bit attached to it. It's absolutely stunning. The company's got 5 of them, and it's used to transport various pieces of a new aeroplane to Toulouse, where they assemble all the wings and the fuselage and everything all goes to Toulouse. Ridiculous, that is extraordinary. Oh, what a privilege!
The last and most critical job of loading a wing onto the Beluga is down to the team, with a tiny bit of help from me.
Are you ready, boys?
Yeah.
We're going forward.
Yeah. Keep that on firmly, unless I shout stop, just let it go. They might have a fault in the aircraft.
You spelt forward wrong.
And I've literally only got inches on each side to play with.
Can you see how close the edge of the wing is there to the aircraft and at the other end? This is the widest part of the wing, the root, you know, the bit that attaches to the fuselage.
This is a big plane. It's the company's workhorse, but despite its size, it can only carry one A350 wing at a time. I've managed to squeeze on board to help deliver our wing. After a 2-hour flight, the Beluga touches down in Toulouse, in the south of France. It's here that Airbus receives thousands of parts from suppliers in Spain and Germany, and the construction of the aeroplane begins, just like a massive Meccano set. Our wing is now carefully unloaded and transported, ready to be attached to the fuselage of the A350.
The site here in Toulouse is 5 times bigger than Broughton, and about 25,000 people work here. But look at this. This is where they start to assemble this fantastic jigsaw puzzle. So you've got the fuselage, the main body where we sit in an aircraft. Then you've got these beautiful wings all the way from Wales being attached. You see the tail fin going in, the horizontal tail plane, the landing gear. It's all coming together, and it's all been done quite quickly. So how many Welsh boys and girls are working in Toulouse?
We've got about 50 altogether.
Yeah.
So we've got design engineers, map engineers, we've also got production, operations, quality.
It's exciting, isn't it? And you, a boy from Mould,
I know.
coming to work
yes.
in Toulouse. Did you ever think you'd end up working in something like this?
No, it's exciting times for me. I've been here for 7 years now.
Yeah.
Family, and I'm still excited. I enjoy getting up for work, I know, yeah.
See how beautifully that's milled there. Isn't that lovely? It's a lovely work.
It's excellent,
As Paul and I get to know each other, we realise we share a surprising link.
I did a course once on milling and lathing in Wrexham Tech.
Very good.
Yeah.
I've been there myself.
You were at Wrexham Tech?
Yeah, a long time ago.
Yeah, well, mine was a bit further back than yours.
Early 80s I was there with Wrexham Football Club, and they used to send us 1 or 2 days a week.
Yeah.
Because it's only across the way, right next to the racecourse ground, so...
Yeah. So we operated in the same grease together then, is that right?
Yeah.
It was quite dirty then though, wasn't it? You know, when it was all, and the stuff spilling out everywhere.
I think it's gone a lot more high-tech now.
Yeah. It's a lot of inspecting to do, isn't it, from the time the wing arrives to when the fuselage comes and it's all fitted? Yeah. So there were, what, 5 test planes?
There's 5 test aircraft, which are on flight test. Yeah. So they do all the different tests that they go through. Yeah. It's a good feat, especially when the first one of these went up last year.
Did you see it?
Yeah, we were excellent, yeah.
When it flew from here?
Yeah, we were all outside
First
here.
Test flight?
First test flight,
yeah. How exciting is that?
Everyone was pushing up.
Yeah, we were pedalling.
No, a sense of achievement, really.
Yeah.
Until this point, the A350 had never flown.
3, 2, 1. Stop.
So imagine the pressure on the test pilots as the whole world looked on.
One check. Positive 5. Gear stays down.
Getting the chance to step inside these extraordinary manufacturing sites makes me realise just how clever we humans can be. I've been told when the paperwork accompanying the aircraft is as heavy as the plane itself, they've got things right. So, when we jump onto an aeroplane to go on our holidays, most of us just take the whole thing for granted.
This is my first look inside the fuselage. Oh, wow. That is stunning. I've never seen anything like this before. I mean, we can see the insulation, all the different coloured insulation. That's to keep us warm as passengers and to stop the noise from coming in as well. And then all the seats go in here. You can see some of the tracks already laid down. This is 67 metres long, the whole fuselage, which is, if you take an Olympic-sized swimming pool, the length of that, and then you add on about 17 metres, about 50 feet, that's how long it is. And this flies over oceans. It's extraordinary. So where are the wings? Well, they're fixed in between the doorways, so you can see here that they're front of this door, and doors to manual, and the second set, graceful, cool, if you like. But that's not why they're fitted. You see, what happens when the aeroplane is flying, you have a much greater static pressure underneath the wing than you do on top. That's how you get lift, that's how the aeroplane rises. But the problem comes at the wing tip, because when these two different pressures of air come together, they create mini tornadoes behind the aircraft, vortices. That creates what's called drag or air friction. And what that means when you're flying a plane is that you need more power to go at the same speed. And if you need more power, you need to use more fuel.
To solve this problem, engineers turned to nature for the answers. This is a tawny Indian eagle. For millions of years, birds have been the perfect flying machines. Airbus employs engineers to study nature, to learn valuable lessons from animals and birds. It's called biomimicry engineering. By studying how this beautiful eagle flies, they have unlocked the secret to the problem of those vortices.
Isn't he stunning? Yes, you. His wingspan is around 2 metres. And he is a bird of endurance because he has to stay on the wing for hours on end looking for his prey, and he can only do that by using as little energy as possible. Now, the A350 engineers have been studying effectively the ruthless efficiency of his wings and using that natural technology or elements of it in the design of the aircraft. So we're going to use, yes we are, and you're going to behave, a slow motion camera to record him flying and then play it back to you, and you can see exactly what happened.
Yeah, it's a very good example. Really perfect aerodynamics.
So an eagle, built for endurance, has to fly on the wing for very many hours, doesn't want to use too much fuel.
No.
Its own energy,
That's
in
right.
fact.
Yeah.
And it's exactly the same principle that's replicated with the wings of the A350.
Yes, well...
Light, with a composite.
It's the very light wing. It means we can adopt some new strategies because we're now using the carbon fibre.
Yeah.
And we couple that with this more detailed understanding of the specifics of the wing shape to get the minimum drag we can. What the Eagle has managed to achieve is the perfect match between a very light, efficient structure and a very efficient aerodynamic shape, with the tips slightly turned up to reduce drag.
Just as the A350 has the winglets.
Just as we've done on the 350.
Yeah.
And you can see the similarities straight away when you see the shots of the Eagle as it comes towards us, how it mimics, well, no, we're mimicking its shape.
Absolutely, yes. It's not mimicking the A350.
It got it right several thousand years ago. It's still with us, so it must be right.
It must be right.
And as we've evolved over 40 years of Airbus wings, you can see innovations coming in, not just in the way we've adapted the shape, but going beyond that to see how the bird actually controls that shape, how it controls itself in flight. And we're now adapting those things into the wings on the 350 as well, so it reacts to its environment. Maybe not quite as effectively as the Eagle, but we're getting there.
And when he's coming into land, flaps down.
Flaps down, wheels out.
Wheels out, gear down.
Eyes on the target.
There's a good boy. There's a good boy.
The new design of the A350 wing reduces fuel burn by 25%. And over half of that saving is by adding these small yet ingenious winglet devices. It has a huge impact on the environment, a greener and more efficient flight, thanks to the Eagle. It's remarkable to think that a whole A350 plane takes just months to build, from a jigsaw of individual parts from factories all over Europe.
And here it is, the first aircraft they've designed and built, which is more than half, 53% in fact, carbon fibre. And I'm standing under one of the incredible wings all the way from Wales, and you think inside the journey in terms of the story that that wing has made. You know, we've got the ribs in there, we have the spar, we have the stringers. It's just stunning. And of course, right at the very end, the upturned wings of the Eagle, the winglets, which make this aircraft so incredibly efficient. One of the best things of all for me is that I get to be one of the very first passengers on board the prototype.
This is one of the 5 A350 test planes to be built, and it's still being used by engineers to test the aircraft to its limits. And where better to go than straight to where I feel at home, the cockpit. Peter Chandler is the chief test pilot at Airbus. He was the brave man who took the very first A350 to the skies in 2014.
Some impressive displays here, Peter. What are you testing in that first test flight?
That first test flight, in fact the first 2 flights, we were what we call opening the flight envelope. So the normal flight envelope, that's from the low speed to the high speed and from low altitude up to high altitude. Just checking the handling of the airplane so that we could actually identify the natural characteristics of the airplane.
What element of the wings has made the most significant difference, do you think, to the A350?
I mean, the design of the wing is state-of-the-art in terms of the aerodynamics, and the fact that we have the ability just to very slightly extend flaps during cruise, so it's basically changing very slightly the camber of the wing, only by maybe 1 or 2 degrees extension of the flaps.
And this is interesting because the control column is over to, well, to the right here, to the left,
yes,
if you're the captain.
Yes, since the mid-80s with the A320, we've had these side sticks as the means of controlling the airplane.
Do you like flying with them?
I find it very comfortable, and it just cleans up the cockpit so much. You've got a nice clear view, and of course the other advantage of having the side stick, if I could just show you, is that it allows us to have a table which has two modes. We have a keyboard in there which is the interface which we can use for example, typing requests for weather, and perhaps the more important setting is that which allows you to eat very comfortably, which is a major concern for all airline pilots.
Ladies and gentlemen, in preparation for takeoff, please fold away your table. Ensure your seat back is in the upright position. Thanks a lot for your attention.
We're taxiing out to the runway now, and the pilot, the captain, has changed the curvature of the wing. So he's put the slats at the front down slightly, the flaps at the back down slightly, and that means that we can take off at a much lower ground speed than we would without this happening. And that's because it provides greater lift at a slower speed. So now, oh, here we go. Off we go, full throttle. He needs to get to what's called the speed of rotation so that he can pull back on the stick. The wings will lift us into the air. It's going to be beautiful. A350, Welsh wings. So quiet. The engines, I'm sitting right next to the engine. And up we go. How beautiful. Very quiet inside. I've got my decibel counter here. It's showing around about 75, 76 decibels, which is, well, if you consider that a normal conversation is around about 70 decibels, that's not bad. But the beauty of the two engines here and the whole configuration of the aircraft is what's called the noise footprint outside. So, you know, when you're sitting at home and you live near an airport, how noisy is the aircraft when it's taking off, particularly when it's at full throttle. And generally, with this aircraft, it's so quiet that the noise footprint is held within the boundary of the airfield, which is astonishing.
I'm not in the cockpit. I'm in front of what we call the flight engineer station. From that station, my job is to conduct the test. So, of course, I'm not able to handle the aircraft because I have no stick, I have no thrust levers.
What kind of things would you be telling the pilots to do?
So the first test we have to do in the first month after the first flight is to do what we call stalls. We have to stall the aircraft, which means that we have to bring the aircraft to a given point where it does not fly anymore.
Okay,
so
that isn't, because a lot of people when they hear stall, they think of their engine in their car stalling. It's nothing to do with the engines. This is all to do with the wings.
Exactly.
Yes.
Finding the aerodynamic stalling point is one of the most important safety characteristics of any aircraft. It's something every pilot has to learn to recover from, but thankfully, Stefan isn't going to be doing it today.
Setting the VORs and,
Like the needles, it's much more difficult.
Yes, absolutely. Do you really like flying this plane?
Oh, yes.
Do you?
Indeed. It's a very beautiful plane and it handles very well, so all the pilots are delighted to fly it.
This is where my story ends. It's been an experience full of surprises and unexpected discoveries. But my full appreciation of how much goes into building an aircraft has only just begun. I'm back in Broughton, and sadly the time has come for me to book my own takeoff slot and fly off home.
This airfield has been at the cutting edge of aeronautical engineering for 75 years, and it had a golden age back in the 1940s. But it seems to me as though it's now within a new golden era. It really is at the forefront of aircraft design on a global scale, and it's fantastic because it's where I grew up, in Flintshire, in North Wales.